Hello and welcome to Sleepy Science. I'm so glad you're here. What if space isn't a stage but a conversation? Threads of entanglement tugging quietly until distance feels like an illusion. Tonight, we'll tug those threads and see how links become wormholes, how minimal surfaces measure information like soap films stretched across a thought. We'll watch tensor networks knit triangles into mountains and let quantum error corrections sew torn patches of spacetime back together. Inside a black hole's hush, we'll glimpse bright islands, then try tiny lab portals where a signal slips through an arch of light. We'll measure time by growth, complexity blooming as volume and action, and rebuild the bulk from the boundary's whisper. We'll rest a moment on the horizon's smooth curve, test it against fire, and sprinkle a droplet that scrambles into 1,000 sparks. Clocks will tick out of order and still agree, and spin networks will count area and volume one quantum at a time. Lattices of cores will stand before geometry. Tetrahedra will condense into a gentle wave. A safe summit will tame the ultraviolet. A second invariant tick will share the dial with light. Rulers and clocks will blur near tiny horizons. We'll lower a probe toward a dark disk and feel radiation push back. Comb soft hair at infinity and watch microstates pull like a warm rubber band. Fog will wash fringes into grain. Two grids will overlap like superposed midnights. Heavy interferometers will paint bars of possibility. Gravity may entangle masses with only its dotted pull. A quiet will rise from vacuum's floor. Tiny ripples will freeze into cosmic rings. And somewhere in the hush, many universes may rhyme at once. If this gentle wander helps you rest, please like and subscribe so more sleepy minds can drift here. Where are you listening from? And what time is it? Now take a slow breath, feel the bed hold you, and let's begin. Entanglement as the fabric of space. You've been taught to picture space as a quiet backdrop, a smooth canvas stretched under everything. But here's a stranger invitation. Imagine that the sense of near and far doesn't come first. It's stitched later by invisible relationships that quantum systems share, so that closeness is less about meters and more about how deeply two parts of the world are correlated. That hunch lives inside a serious research thread where entanglement, the quantum linkage that lets two systems behave like one even when separated, doesn't just decorate space, it helps define it, and once you sit with that possibility, familiar ideas begin to tilt in useful ways. Start with what entanglement actually is, because it isn't telepathy or a faster-than-light whisper. It's a precise pattern in the joint description of things. When two photons, atoms, or small patches of a field are prepared together, neither piece alone carries a full story, but the pair does. So measuring one predicts what a matching measurement on the other will yield, not because a signal flies, but because the outcome was encoded in their shared state from the beginning. Make this concrete by thinking beyond a pair. Tile the universe into many tiny regions, and ask how much any region knows about its neighbors. If two regions are richly entangled, learning about one reduces your uncertainty about the other, and if entanglement is sparse, your predictions fail. Now imagine a map built not with rulers, but with a rule. Place regions closer when their entanglement is stronger, and a geometry starts to emerge from pure bookkeeping of correlations, the way a social network's dense clusters hint at neighborhoods without a street map. That plain idea grows teeth because certain quantum systems obey area laws, where the amount of entanglement between an inside and an outside scales with the size of the boundary rather than the volume, a pattern that rhymes with the way black hole entropy scales with horizon area. And that rhyme isn't cosmetic. It guided decades of progress linking gravity to quantum information. In some strongly studied models of the universe, especially those with a clean boundary where the full theory lives and an interior that behaves like a gravitational world, you can use entanglement measures on the boundary to calculate geometric features inside. So a number that quantifies how much is shared lines up with how much area a surface has, which is a startling hint that the shape of space responds to the structure of information. Even if those models don't copy our cosmos exactly, they supply a working lab for the claim that geometry can be read off from entanglement patterns, and once you accept that, you can reverse the perspective you grew up with. Perhaps fields and matter don't move through a pre-given stage, and then occasionally become entangled. Perhaps the stage is the large-scale appearance of who is entangled with whom, with gravity emerging as the elastic way that stage reacts when energy and information shift. You can test the edges of this idea without heavy equations. Ask how entanglement spreads after you poke a quantum many-body system, and you'll see light cone-like fronts of correlation, growth in experiments with cold atoms and trapped ions, as if a fabric were being tugged locally and the tug propagated outward at a characteristic speed. And ask what happens in ground states of gapped materials, and you'll see the same area law signatures that make geometry feel smooth rather than ragged. At the same time, intellectual honesty matters. No one has proven that entanglement literally is the fabric of our universe's space, and the bolder slogan that links are bridges is a provocative conjecture, not a finished fact, but the body of evidence from exactly solvable models. Numerical simulations and cross-checks between information flow and curvature keeps pointing in a coherent direction. What makes this worth your attention isn't mystique, it's utility. Thinking in terms of correlations unifies puzzle pieces that once felt unrelated. Why horizons store information on surfaces? Why cutting a system in two costs you knowledge mostly along the cut? Why repairing local damage in certain quantum codes feels like mending a tear rather than recreating a whole dress? The practical moral lands close to home. If nearness in the deep sense is built from shared information, then rearranging correlations is a way of redrawing the map. Entangling distant parts can make them effectively closer in the emergent geometry of a model, while losing entanglement can thin the fabric and push regions apart. And this is more than poetry, because toy constructions that glue many small quantum pieces together with the right pattern really do produce spaces with recognizable distance, area, and sometimes even dynamics that mimic gravity. You don't need to worship the details to feel the shift. Space starts to look less like a rigid container you inhabit, and more like a living tapestry whose weave updates whenever matter interacts, thermalizes or scrambles information. And once that intuition settles, older confusions loosen their grip. Asking where something truly is becomes less meaningful than asking with which degrees of freedom is it most entangled, and worrying about signals. Crossing vast gulfs gives way to tracking how correlations route through a network that may curl the gulf inward. Still, keep your feet on the ground. This program is strongest in controlled settings and simplified universes, and mapping it cleanly onto our expanding, messy cosmos remains an open, beautiful problem. But the next time you hear that two systems share a quantum state, try swapping your picture. The link is not a thread stretched across a pre-drawn void. The link may be the reason the void looks connected there at all. And as that idea fades to quiet, notice how it changes your posture toward the unknown. You are not simply drifting in a cold room of coordinates. You are part of a pattern that helps set the room's shape, a participant in a web that holds you and that you, in a small but real way, help to hold. Wormholes and links. You picture two cliffs facing each other across an impossible canyon, and wonder whether a hidden footbridge could ever be real. And the honest answer is both stricter and more interesting than science fiction. General relativity allows space-time geometries with bridges connecting distant regions. Einstein and Rosen wrote down such a solution nearly a century ago, but the original bridge pinches off too quickly to cross, more like a mirage in the math than a tunnel you could walk through. And making a wormhole that stays open demands something nature rarely provides at scale: a sustained patch of negative energy that pushes space outward instead of letting gravity squeeze it shut. This isn't a license for fantasy so much as a guide to what must be overcome, because the ordinary stuff in stars, planets, and people obeys energy conditions that keep gravity well behaved, and those conditions slam shut most shortcuts. Yet at the quantum level, tiny exceptions exist. The Casimir effect, for example, can create brief regions where the energy density dips below the usual baseline. So the question becomes not, is negative energy possible, but can you marshal enough of it in the right shape for long enough without wrecking causality? And on that front, we have clever ideas and stark limits. Classical wormholes that you could traverse safely remain outside our engineering reach for good reasons. The amounts of exotic stress you'd need explode to astronomical values as the opening grows. Any leakage of normal matter tends to make the throat collapse, and attempts to fold such a tunnel into a time machine trigger deep consistency problems that most physicists expect nature to forbid. Yet none of this makes wormholes an empty topic, because they serve as a microscope for principles you can actually test. How gravity handles information, how horizons store and release it, and how quantum correlations can act like links that are not roads, but still connect distant doings in precise, measurable ways. This is where the phrase links deserves care. In some modern models that tie together quantum theory and gravity, two systems that share strong correlations can be described in geometrical language as if they were joined by a thin bridge. Not a highway you can send a person through, but a relationship that lets a carefully prepared signal slip across under strict rules. And theorists have even shown how to momentarily prop open such a bridge in a controlled setting by nudging the two sides with a coordinated interaction. Think of it like passing a note between two rooms through a slot that only opens if both rooms tap the wall in the right rhythm. Experiments have sketched versions of this idea using small quantum processors that simulate the dynamics of a toy gravitational world, where a pattern of operations on one chip causes a distinct, time-gated response on another that matches the signature expected from a traversable wormhole in the model. The key word is simulate, because no one has built a literal tunnel in our space-time, but the lab behavior tracks the same logic. Correlations and couplings can guide information along surprising routes without breaking the light speed limit or letting you send a warning to your past. Once you separate the dream of star-hopping portals from the reality of lawful links, the science becomes more gripping. A wormhole is a shape in a solution of Einstein's equations, a proposal for how geometry could connect far places, while a link is a pattern of relationship that tells you what influence can flow, where and when. And the second notion shows up everywhere, from black hole thought experiments to condensed matter systems, where entanglement stitches distant regions into an effective whole. Practical questions follow. What would you measure if the universe offered a microscopic bridge? Lensing patterns that twist light oddly, echoes in gravitational waves, or unusual delays in signals that thread a curved detour? And could quantum fields supply just enough negative energy in a narrow channel to permit a single, low-energy message to cross without inviting paradox, as some calculations suggest? At the same time, clarity requires boundaries. No confirmed observation has revealed a natural wormhole. No credible scheme lets you stabilize a human-sized one with present or foreseeable technology. And every construction that toys with time loops bumps into walls built from thermodynamics, quantum uncertainty, and the stubborn bookkeeping of cause and effect. Still, the links perspective reshapes your expectations in a healthy way. Rather than hunting for literal tunnels, you start tracing how correlations, couplings, and carefully timed operations can make distant systems behave as if they share a short path. And with that shift, you can read recent progress correctly. Laboratory platforms that emulate curved spacetimes, measurements that chart how information scrambles and then partially unscrambles, protocols that turn a pair of chaotic systems into a conduit for a fragile signal, all without any object outrunning light or any law getting cheated. The deeper lesson is about humility and precision. Nature seems willing to surprise you with shortcuts in description, where a messy, many-body problem becomes a clean, low-dimensional geometry, and with shortcuts in influence, where the right relationships let you recover a message that looked lost. But she guards the bedrock rules that keep predictions consistent. So the real drama is not whether you can jump galaxies by stepping into a glowing ring. It's whether geometry and information are two sides of the same coin, and whether learning to shape the links in complex quantum systems will someday let you route signals, computations, and even heat flows through structures that feel, in their behavior, like tiny, well-behaved wormholes. And when the lights dim after this mental walk, the canyon in your mind is still there. But now you know the bridge that matters first is not a tunnel through space. It's a lawful connection between causes and effects, tuned by correlations and timing, miles from fantasy and inches from devices we already build. A reminder that the universe often grants you new routes, not by breaking its rules, but by showing you new ways to use them. Holographic entropy and minimal surfaces. You draw a loop on the skin of a world and ask a simple question: how much can the inside still surprise you? And the remarkable answer is that, in certain precise theories of gravity, a geometric surface stretched into the interior tells you exactly how much uncertainty remains, so that a number about missing information is computed by the area of a minimal surface that hangs from your loop like a soap film. To feel this without equations, picture a wireframe dipped into soapy water. The film that forms finds the shape with the least area consistent with the boundary, and in holographic models, a similar film, pulled taut through the curved interior, measures the entanglement between the region on the boundary and everything else, turning a slippery information concept into a ruler you can lay on a surface. This is not a vague analogy, but a sharp rule in a large class of examples. Choose a region along the outer edge where the full quantum theory lives. Then look for the interior surface that anchors on the region's boundary and has the smallest possible area while staying properly connected to it. And the area of that surface, after the usual unit conversions, equals the region's entanglement entropy, an information measure that says how intertwined the region is with its complement. The power of this rule comes from how many puzzles it knits into one fabric. Because black holes long ago taught us that gravitational systems count information in units of area rather than volume. And here the same theme reappears cleanly for ordinary regions. The leading contribution to entanglement scales like the size of the dividing surface, not the bulk of the stuff, which is why the soap film picture is more than pretty. It's diagnostic of how nature parcels correlations. Crucially, the minimal surface does more than return a single number. By moving the boundary region around, splitting it into pieces, growing or shrinking it, you can watch the soap film reshape and from those changes, read timeless information principles. When two nearby regions share a boundary, the combined minimal surface area tells you how their uncertainties relate, and well-tested inequalities in information theory show up as geometric comparisons between areas, so that a statement like "the whole is at least as uncertain as the sum of its parts minus their overlap" becomes a triangle-like relation among surfaces. Even more striking, the surface doesn't just dangle in empty space. It marks the edge of what's reconstructible about the interior from the chosen boundary region, a zone often called the entanglement wedge, and that gives you a practical handle. If your soap film passes around a clump of interior matter, then, in principle, records at the boundary region are enough to rebuild what happened in that clump, whereas if the film skirts around it, you cannot fully recover those details from that region alone. This "who can know what" map is dynamic. If the interior geometry bends because energy moves, or if you change which boundary qubits you control, the minimal surface can jump from one path to another, a sharp geometric transition that mirrors a sudden regrouping of which degrees of freedom are most entangled with which. Researchers have watched these jumps in solvable models and in numerical experiments, and they show up as kinks in entropy curves that match expectations from quantum many-body physics. The soap film picture also helps you think about time. When the state evolves, you generalize minimal to extremal, allowing the surface to sit in a mixed slice of space and time, where its area is stationary rather than merely smallest. So the recipe keeps pace with dynamics without asking you to rewrite the theory from scratch. Not every geometric intuition is unique. There is a complementary bit threads picture where you imagine incompressible flows through the bulk, and the maximum number of strands that can pass from the region to its outside equals the same entropy, but that dual view only deepens the message. Information measures and geometric bottlenecks are two ways of describing one constraint, and whether you see a film with minimal area or a bundle of non-crossing threads at maximal flow, the answer is the same because both encode how much correlation can fit through the interior. Practical payoffs keep emerging. By adding or removing matter, you can test how the minimal surface bends and thus probe how energy and information together shape the interior. Push mass into the bulk and the surface tends to bow outward, increasing area, and therefore the boundary's uncertainty about the inside, while pulling mass away can allow the surface to slip inward and lower the count. And in settings where two boundary regions are far apart, the surfaces they respectively anchor may merge or separate depending on how strongly the interior ties them, offering a geometric proxy for transitions between mostly independent and noticeably connected. Importantly, none of this grants you a way to send messages faster than light or to beat the bookkeeping that keeps cause and effect consistent. The surfaces respond to the lawful evolution of the state. They don't rewrite it, but the dictionary they supply is astonishingly efficient. A computation that would be forbiddingly hard if you tried to track every quantum degree of freedom becomes a problem in differential geometry. Find the right surface and read off its area, and the answers pass stringent checks from both sides of the duality. It's fair to ask how literal this is for our universe, which does not obviously come with a neat boundary where a perfect theory lives. And the honest answer is that the correspondence is best understood in highly symmetric toy worlds that nevertheless capture essentials about gravity, strongly interacting matter, and how information flows in complex systems. Still, the lessons travel well. Area laws appear widely in ground states of gapped quantum systems. Minimal surface-like objects diagnose bottlenecks in networks and error-correcting codes. And the intuition that what you can learn is controlled by the narrowest place your knowledge must pass through proves useful from black hole physics to quantum devices. The quiet beauty here is the unity of ideas. Entropy, which sounds like disorder, becomes a clean curve you can trace with a film. Geometry, which seems purely spatial, turns out to summarize questions about knowledge. And reconstruction, which feels like data science, becomes a matter of which surfaces touch which regions. When you step back, the message is gentle but firm. If you want to know how much of a world is accessible from apart, look not at the volume you hope to command, but at the boundary you must cross. Because in holographic settings, that boundary is everything, and the minimal surface you can hang from it is your honest measure. Let that sink in as a closing thought. Sometimes the shortest answer to "how much can I know" is not an equation, but a surface you could almost imagine touching, a quiet film that tightens until it tells you the truth. Tensor networks building geometry. You begin not with a spacetime diagram, but with a box that eats indices and spits out relationships. And while that sounds abstract, it's the most down-to-earth way to build worlds from the inside out. A tensor is simply a multi-entry table that tells you how several pieces of a system lean on one another, and a tensor network is what you get when you connect many of these tables by their shared entries, so that outputs of some become inputs to others, turning raw data about local relationships into a web that represents an entire quantum state. The surprise is how far this humble recipe goes. By wiring small, repeated blocks with care, you can capture materials, molecules, and model universes that would otherwise be impossible to store in a computer. And you can do it in a way that makes structure visible. Short, tidy chains encode one-dimensional matter where correlations die off quickly. Sheet-like grids capture two-dimensional habits. And branching, layered networks carve the world into scales so that nearby wires describe nearby physics, while deeper layers summarize broader patterns. If you've heard that real quantum systems are too large to simulate, this is the answer we've learned to give. Most systems of interest don't explore their astronomically huge possibility space. They live on a small, structured ledge defined by how entanglement behaves, and tensor networks are maps of that ledge, efficient because they store what matters, who is tied to whom and how strongly, without drowning you in everything else. Now, translate this efficiency into geometry. Lay a network on a page, place the elementary degrees of freedom along the rim like a boundary, and let the interior wires and boxes be your bulk. And then do something that feels like cheating but isn't. Define distance by how many bonds you must cut to separate two parts, or by how many steps a signal has to climb through the layers to get from one point to another. Suddenly, the drawing behaves like a space. Paths have lengths, regions have bottlenecks, and the difficulty of splitting the network mirrors how hard it is, physically, to disentangle the corresponding pieces of the system. In simple chain networks, the shortest path between neighbors is short because only a few bonds connect them, matching the idea that close things share strong, direct correlations, while far apart sites require you to cut more bonds, matching weaker, more mediated ties. In layered branching networks, designed to remove short-range clutter at each step, an approach often called entanglement renormalization, the layout naturally resembles a curved space where the boundary has many more points than the interior can easily reach, so geodesic-like routes bend inward, and two boundary patches that look adjacent along the rim may, in the interior, connect only high up the tree after several layers of processing, just as in a negatively curved space where neighborhoods separate quickly. None of this is mystical. The boxes represent isometries and disentanglers, operations that compress redundant information and peel away local tangles so that what remains at deeper levels is the long-range structure. Because these boxes are arranged hierarchically, the network has a causal sense. Perturb one site and only a wedge of boxes needs to update, so that cause and effect become visible as a cone spreading through layers, a clean echo of how influences propagate in a spacetime with an arrow and a speed limit. More than metaphor, this picture computes the number of bonds crossing a minimal cut through the network upper bounds, the uncertainty you'd assign to a boundary region. So counting lines in a diagram provides a quick estimate of how much that region is entangled with the rest, and rearranging the network, adding layers, widening trunks, changing the branching factor, changes those counts the way reshaping a landscape changes distances and areas. Engineers exploit this every day in algorithms with unromantic names. By choosing a chain-like structure for problems where correlations are local, one method solves quantum magnets with near-textbook accuracy on a laptop. By switching to grid-like layouts, chemists approximate electrons on surfaces. By using layered trees, researchers compress states that carry patterns across many scales, and in doing so they discover that good geometry in the network. Short routes for relevant signals, narrow wastes where information must pass, predicts good physics, meaning accurate energies, realistic correlation lengths, and phase diagrams with the right shape. Like any craft, the art lies in choosing the right scaffold for the job. If your system hosts long strings of correlation, your network should offer long, cheap corridors for those strings to run. If your system forms islands connected by rare bridges, your network should reflect that with sparse trunks and occasional crosslinks. And if your system is expected to behave like a curved interior glued to a busy boundary, your best shot is a layered, hyperbolic-flavored tiling where every additional ring outward adds exponentially many boundary sites, matching the intuition that one interior step corresponds to many degrees of freedom at the edge. This is where geometry truly emerges. The network is not drawn to mimic a space you already know. It is trained or constructed to match the relationships in the data and the geometry you read off afterward. How quickly neighborhoods blow up, how narrow the wastes are, how deep the layers go, is a diagnostic of the physics rather than a premise. Skeptics rightly ask what keeps this from being just a pretty drawing, and the answer is performance and prediction. When you tune the network to match what experiments see, correlation functions that decay in a particular way, spectral gaps of certain sizes, the same network can forecast responses you haven't measured yet, like how the system will react to a local quench or how a defect will pin order, and those forecasts can be checked. Even the limits are instructive. When a material enters a highly entangled, volume law regime where every piece shares with every other, simple networks struggle because the number of bonds you'd need explodes, a warning that your geometry has thickened. The easy corridors are gone, and you must either enlarge the building blocks or change the architectural style. Ideas that push people toward more expressive networks or toward hybrid designs that borrow tricks from machine learning. Practical experiments now speak the same language. Cold atom platforms arrange dozens or hundreds of sites with programmable interactions, and their measured patterns of correlation and growth over time are fit and forecast by networks that compress the dynamics. Ion trap groups map out how information spreads after a local kick and compare the observed light cone-like wavefront to what a layered network predicts. Even error-correcting codes, the backbone of resilient quantum devices, can be viewed as tensor networks where logical information lives at the top and is fanned out through isometric boxes to many physical qubits at the bottom, so that local noise clips a few leaves without chopping down the trunk. Step back and the moral is gentle but radical. A tensor network is a manual for knitting complexity into shape, And when the knitting is faithful to the rules a system obeys, the shape behaves like a space in every way that matters for prediction: paths, cones, bottlenecks, and all, so that asking where inside the network becomes the same as asking at what scale and through which pathways the system organizes its knowledge. This doesn't prove that our universe is literally a tensor network, and you should keep a clear boundary between metaphors and measurements, but it does prove something you can use today. When the world you study is too large to hold all at once, build it from small, honest relationships, and let those connections decide the geometry for you, because the shortest routes to understanding are rarely drawn beforehand. They are discovered when you connect the right pieces and count the bonds that truly matter. Quantum error correction is space-time glue. You don't keep a message safe by locking it in one place. You keep it safe by spreading it so widely that no single accident can kill it. And that simple idea is the heart of quantum error correction and the reason some physicists say it behaves like a kind of glue for space-time. In a quantum device, the information you care about is not stored in one fragile element, but woven across many physical elements, so that small bursts of noise, losses, or flips can be detected and reversed without ever touching the protected message itself. And when you translate that logic into models where gravity emerges from deeper quantum degrees of freedom, the same redundancy looks like the mechanism by which a region of space holds together despite local damage, as if the stability of a place were backed by the way its information is distributed. Begin with a clean picture. Think of a sentence written not on one sheet, but scattered as overlapping fragments across a stack of papers, where any single page is unreadable but several together let you restore the text. And now, trade paper for qubits. Quantum error correction takes a tiny pattern you want to preserve and encodes it into a larger pattern of many parts, so that if a small number of those parts are corrupted, you can diagnose what went wrong and undo it by consulting simple checks that never pry open the secret itself. This is not hypothetical technology, but today's laboratory craft. Surface codes lay out qubits like tiles on a floor and ask local questions, tiny arithmetic tests that flag where errors have likely struck, and hardware teams run these tests in loops, correcting in real time and pushing their machines toward thresholds where the protected information can, in principle, live indefinitely. The twist that turns engineering into a window on space-time is how these codes organize access. No small patch of tiles can reveal the logical secret, because the code insists you gather a big enough region before recovery works. And that rule maps neatly onto a gravitational dictionary where how much of the boundary you control decides how much of the interior you can reconstruct, so that the very idea of a place, what events inside it can be determined from outside records, becomes a property of how information is redundantly stored. Make this concrete without equations. Take a round boundary and designate a sector as yours. Then ask which interior events you can, in principle, rebuild from the data available in that sector. The answer is not arbitrary. It is controlled by whether the erasures outside your sector are within the code's tolerance, and the frontier separating what you can recover from what you can't is pictured by a surface in the interior that behaves like a bottleneck. Move the boundary cut and the frontier slides, sometimes jumping when your sector becomes large enough to support a different recovery strategy. A crisp transition in what counts as part of your wedge of influence, and you can follow these jumps in exactly solvable toy models and in network codes built by hand, where the number of links you must cut to isolate a region sets the scale of correctable erasures. Notice what this buys you. Local scrapes and dents, small bursts of noise on the boundary, do not tear the interior message to shreds, because the logical content is stored non-locally, smeared across many boundary parts in a way that any one of them can help hold the whole together. And that is why people call it glue. The code makes the interior robust to local loss, so the place survives even when some bricks chip. There is a second payoff that is easy to miss. Complementary recovery, where two different boundary regions, each large enough but disjoint, can reconstruct different, non-overlapping aspects of the same interior without contradiction. The way two different committees can each verify separate chapters of a report. And this property fits beautifully with gravitational expectations, that no single observer can access all interior details at once, but different observers can consistently recover what lies within their causal reach, that elegance doesn't grant superpowers. No one can send a message faster than light or read information from a region they do not control, and the code never lets you learn a protected secret by asking the wrong question. The checks tell you which correction to apply without revealing the message. So causality and privacy remain intact, but within those guardrails the code provides a flexible blueprint for resilience, and the blueprint has already changed how we think about deep puzzles. For example, if you imagine an interior excitation, call it a bulk bit, and then ask which boundary region can reconstruct it, you discover that the answer depends on how the code has spread the logical degrees of freedom. Small boundary caps cannot recover deep bulk excitations, while larger caps can, and pushing matter around inside shifts these recovery regions in a way that mirrors how gravity focuses or defocuses light, suggesting that the shape of space is nothing more than a summary of which logical bits are recoverable from which boundary collections. Even the act of falling behind a horizon takes on an informational face. Adding energy in the interior changes which boundary checks are reliable, bending the frontier of recoverability the way a massive object curves nearby paths. And asking whether a boundary observer can still reconstruct a fallen diary becomes a precise question about whether the necessary checks survive the noise, not a mystical paradox about loss. Skeptics will rightly ask how literal all of this is for our universe, which shows us no obvious boundary theory we can program. And the fair answer is that the sharpest statements live in controlled, highly symmetric models that nevertheless capture key traits of gravity and strong interactions. But the core morals travel beyond those playgrounds. Redundancy protects meaning. Locality of checks enforces a notion of neighborhood. And the capacity to recover after small erasures is what turns a brittle collection of parts into a coherent region that deserves to be called a somewhere. You can test these morals in hardware as well as on paper. Teams now run small codes in superconducting circuits and trapped ions, injecting deliberate errors and showing that the logical content emerges intact when the checks point to the right repair, and the same mathematics that schedules those repairs appears, almost unchanged, in the diagrams we draw to reason about emergent interiors. Taken together, the picture is modest but powerful. The world may not literally be a computer code, but the way information is distributed and protected seems to decide what persists as a place and what dissolves as noise. And quantum error correction gives you a language to say that clearly. How big a scar a region can tolerate, which observers can rebuild which events, and why the most reliable truths about a complicated system are often the ones stored redundantly across it. Let that sink in as the closing pulse of this idea. If space-time feels like something that can sag, stretch, and yet hold, perhaps that feeling is the echo of a deeper rule. That meaning spread widely is meaning that endures. And quantum error correction is the rulebook that turns that echo into a plan, not just for future quantum machines, but for any theory that hopes to explain why a universe with noise can still have places that last. Islands in black hole evaporation. You watch a black hole glow faintly and think of it as a one-way story. Things fall in, heat seeps out, and information disappears behind the curtain. But if you keep track of the uncertainty carried by that heat over time, you stumble on a curve that refuses to accept loss as the ending. At first, the uncertainty rises, as if each particle of radiation were a new rumor with no source to check. And then, if the world is truly unitary, it must turn over and fall, ending at zero, as if the rumors together reconstruct the whole truth. This turnover is the page curve, long predicted, but stubbornly incompatible with the original Hawking calculation, which said the uncertainty should just keep rising until nothing knowable remains. A result that made physicists uneasy for decades, because it suggested either quantum mechanics breaks down for big objects, or black holes somehow shred information forever. Islands are the modern concrete fix to this tension, and they arrive with a counterintuitive message. When you compute the uncertainty of the radiation you hold far away, you must include in the accounting a carefully chosen chunk of the region that you thought was locked behind the horizon. A chunk called an island, and once you do that, the curve behaves properly. rising early on when the radiation is just noise, then bending and falling after a characteristic moment known as the page time, finally returning to zero as the radiation purifies. This is not hand-waving or a trick of words, but a statement about what you are allowed to count as part of your system when gravity is involved. And the rule comes from a path integral analysis of many copies of the problem in which new connections, absent in simpler field theories, appear between histories and change, which internal regions are tied to which external measurements. The practical recipe is simple to say even if it took years to derive. To find the entropy of the radiation you collect, try adding a candidate island just inside the black hole. Compute a generalized uncertainty that includes both the interior area contribution and the ordinary quantum uncertainty of fields, and then choose the island that makes this combined quantity as small as allowed. Early in the evaporation, the best choice is to include no island at all. Your radiation is independent noise, and the uncertainty rises. But after the page time, a tiny interior region suddenly becomes part of what you know, and including it makes the overall count drop. Because this interior chunk carries precisely the correlations that knit the radiation back into a single consistent story. You can watch this happen in solvable models of near-extremal black holes, where the geometry is simple and the method is clearest. Before the turnover, your ignorance is priced by what is outside only, and after the turnover, your ignorance is priced by a competition between exterior mess and interior area, with the interior winning just enough to pull the curve down. What makes the idea trustworthy is the weight of cross-checks, independent methods that had nothing to do with the original paradox, calculations in simple quantum systems that mimic black holes, studies of how randomness spreads in strongly coupled matter, and careful comparisons with expectations from ordinary quantum mechanics line up with the island prediction, all pointing to the same moral that gravity changes bookkeeping for subsystems in a lawful way rather than destroying information. It is crucial to be clear about what islands are not. They are not tunnels for messages, not portals you can step through, and not an invitation to violate causality. No observer can pluck a diary from behind the horizon just because a formula says a small interior region now counts as part of the radiation's description. And no one can use the island rule to send warnings into their past. Instead, think of the island as a statement about correlations, about which interior degrees of freedom are in principle reconstructible from faraway records, so that the boundary between what the radiation can reveal and what it cannot moves inward as more radiation is collected. The timing of that inward move makes physical sense. Information about the early info is dribbled out in a scrambled, hard-to-decode way, but by the page time, the later radiation carries enough redundancy to start cancelling uncertainties from the earlier batch, and the best description of the radiation system then includes an interior partner region, because that is the honest way to count how much of the total state you effectively control. The mathematics that justifies this picture introduces new geometric saddles, nicknamed replica wormholes, that couple different copies of the system in the path integral. And while that phrase sounds exotic, the message it delivers is grounded. Gravity alters which partitions of the world are meaningful, especially when horizons are present, and once you adopt the gravity-aware partition, standard quantum mechanics takes care of the paradox. The approach has teeth beyond drawing a pretty curve. It predicts, when the turnover happens, how large the late-time entropy should be, and how the edge of reconstructability moves as the black hole shrinks. And these predictions survive changes in the details of the model, suggesting the lesson is generic rather than a curiosity of one toy universe. The island idea even reframes old questions in a cleaner way. Ask whether a distant observer can in principle recover a message thrown into the hole long ago, and the answer becomes yes, but only after the page time, and only with a decoding task that may be punishingly hard, turning a philosophical worry into an engineering challenge about complexity rather than a violation of laws. It also sharpens the status of dramatic proposals like firewalls by reminding you that what different observers can reconstruct need not agree on a single, naive split of the Hilbert space. Who can access which correlations is observer-dependent in gravitational settings. so apparent. Contradictions often melt when you compute the right entropy for the right partition. Still, humility is healthy. We do not yet have direct experiments with astrophysical black holes that measure fine-grained entropy, and the crispest derivations of the island rule live in highly symmetric, lower-dimensional models chosen for calculational control, but the consistency of the story across methods and the precision with which it matches the expected page curve make it the most compelling resolution of the information puzzle on the market. The quiet lesson you carry away is that ignorance, in a gravitational world, is not just about what you refuse to look at. It is about which pieces of the world are legitimately part of your system once geometry and quantum mechanics share the stage. And when you let that lesson in, the black hole stops being a shredder of meaning and becomes a careful accountant, paying out secrets late, in full, and only after you have collected enough of the ledger to balance the books. Traversable wormholes in lab models. You don't need a cosmic tunnel to study a traversable wormhole. You need two small, well-controlled quantum systems that you first lace together with just the right shared state, and then tap in sync, so a fragile message can slip through a brief, lawful opening. And while that sounds like sleight of hand, it's a clean, testable protocol that laboratories have begun to emulate. Start with a pair of chaotic but programmable systems prepared in a special, highly correlated state, then encode a tiny probe, a single qubit or a faint wave packet, into one room and, before chaos scrambles it beyond recognition, deliver a coordinated nudge to both rooms. If the nudge has the correct sign and timing, it creates the effect, in the model's gravitational language, of a pulse of negative energy threading the space between the rooms that briefly props open a throat, and the probe emerges on the far side within a predictable time window, where you can read it out and check that you got back what you sent. None of this breaks causality or lets you outrun light, because the opening is not a hole in our spacetime, but a controlled change in the joint dynamics of the two systems that reroutes information through correlations already present. And the classical data you use to coordinate the nudge is precisely what keeps the process honest. No message crosses without that external handshake. In practice, teams build the two rooms from platforms like superconducting qubits, trapped ions, or photonic circuits. And they choose dynamics that are chaotic enough to mimic the way gravity scrambles information near a horizon, yet structured enough to be programmable, with one especially popular sandbox using interacting units that behave like the famous SYK toy model of quantum chaos. The recipe unfolds in 3 steps you can follow without equations. Prepare the pair in a maximally helpful shared state, so that each side holds a compressed mirror image of the other's patterns. Let the left room swallow the probe and begin to scramble it. Measurable diagnostics like out-of-time order correlators confirm that the message is rapidly spreading across many degrees of freedom. Apply a brief, carefully tuned interaction between the rooms, the double tap, whose sole purpose is to convert that otherwise lost, delocalized information into a form the right room can decode, and then look for a sharp peak in a simple 2-point measurement on the right that arrives inside the predicted window. When experiments hit the timing and sign just right, they see the signature rise out of the noise, a detectable recovery of the probe on the far side, with fidelity limited by the usual enemies, finite size, decoherence, and imperfect calibration, but still beating the best you'd expect if no traversable channel had been opened. Crucially, the same protocol fails on demand if you flip the sign of the nudge or mistime it, underscoring that you aren't watching a vague entanglement magic trick, but a concrete, reversible routing of information governed by parameters you control. To keep your intuition grounded, translate the gravitational story back into circuit language. The initial shared state is the entangled resource that makes teleportation possible. The coordinated nudge is the classical message you must send to make teleportation work, and the recovered probe is the teleported state. So, opening a wormhole in these lab models is literally equivalent to running a specialized, chaos-aware teleportation protocol whose spacetime picture happens to look like a traversable throat. This equivalence is not just poetic, it's protective. It guarantees there's no way to turn the setup into a time machine, no way to signal into your past, and no way to send anything at will without paying the price of the coordinating data. Because the teleportation viewpoint forces you to respect the bookkeeping of cause and effect. The scientific payoff is twofold. First, you gain a new kind of knob for probing scrambling, because whether the probe gets through depends sensitively on how fast and how far the initial system spreads information, and the recovered signal tracks that invisible growth in a direct operational way. Second, you get a working laboratory for questions that used to live only in thought experiments. How a small, deliberate injection of negative energy-like influence changes what is reconstructible, how a brief window of traversability opens and shuts, and how noise ruins the corridor by injecting the wrong sign of energy at the wrong time. There are honest caveats that make the story better, not worse. Current devices are tiny compared with the vast limit where a clean geometric picture emerges. So the wormhole you simulate is a metaphor you earn by matching many independent signatures. Timing of the peak, dependence on nudge strength, suppression under the wrong sign, consistency with scrambling diagnostics. Not a literal tunnel you could fly a camera through, and some platforms achieve the effect in a heavily simplified, error-mitigated regime that emphasizes clarity over scale. That said, the ability to open and close the channel at will, to vary the amount and direction of the injected influence, and to watch the probe's survivability degrade with controlled noise gives you a sturdy checklist for did we really do it, and those checks keep coinciding with expectations from the traversable wormhole theory. Perhaps the most quietly useful lesson is methodological. By designing dynamics so that geometry is the best language to describe them, you turn hard-to-see properties, like how operator size grows during chaos, into distances and transit times you can measure. And by adding a minimal, classical coordination line between subsystems, you convert a hopelessly scrambled message into a decodable one without cheating any laws, which is exactly the spirit of modern quantum control. As devices scale and stabilize, you can imagine richer versions of the experiment, sending multi-qubit messages and watching which shapes survive, testing how long the window can be held open before the background chaos eats it, exploring whether clever encodings make the corridor more fault-tolerant, and using the same machinery to study how heat or entanglement flows along constrained routes in materials. When you step back, the philosophical punchline lands softly but firmly. No lab has ripped a hole in spacetime, yet laboratories are already routing information through lawful shortcuts that behave, in every trackable way, like a tiny, traversable throat within a model gravity world. And that is enough to change the way you think about both. Gravity becomes a language for complex quantum dynamics, and complex quantum dynamics become a tool for rehearsing gravity's strangest conversations, all without leaving the confines of a chip, an ion trap, or a dark optical table where the only portals are the ones you program, and the only miracles are the ones you can reproduce on demand. Complexity, volume, and complexity action conjectures. You've measured time with clocks and space with rulers, but there's a third yardstick that modern physics keeps reaching for. How many simple steps does it take to build a state, or to undo what dynamics have done? And the daring claim behind the complexity volume and complexity action conjectures is that, in certain gravity setups, that number of steps is mirrored by a tangible bulk quantity, either the volume of a special interior slice or the total action of a space-time region. Start with the itch that created this idea. Black holes don't just sit. Their interiors grow for a long while, even after the outside looks steady. And ordinary thermodynamic counts don't explain that quiet swelling. So theorists asked whether the unseen growth might track something more operational. The minimal number of easy gates a quantum computer would need to prepare the evolving boundary state from a simple reference, which we call its circuit complexity. Now translate that into geometry you can picture without equations. Pick a nice space-like slice that threads a two-sided black hole, one that runs from one boundary to the other through the interior, and let its volume be your bulk measure. Then, as boundary time advances, that volume grows roughly linearly for a large range, just as circuit complexity is expected to grow linearly under chaotic dynamics, until it finally saturates at a dizzying height. The alternate recipe uses not volume but action, the integral that summarizes how space-time curves and matter moves. evaluated in a region called the Wheeler-DeWitt patch, the union of all points that can both influence and be influenced by a given moment on the boundary. Remarkably, this action also grows in time in the models where we can check, and the rate of growth aligns with expectations from the computational side, up to bounds that say you can't process or assemble useful changes faster than a certain limit per unit energy. What makes these proposals more than poetic is how many telling features they unify. When you kick a black hole with a burst of energy, a shock that injects simple information, the complexity on the boundary jumps. But the interior growth seen by either bulk measure pauses briefly before resuming with an offset, a phenomenon nicknamed the switchback effect, which matches circuit intuition that some of what you just did can be unwound by the backward part of the evolution, reducing the net cost for a short window. As time unfolds, both pictures predict a long regime of steady increase tied to the system's scrambling behavior, the way initially local information spreads into global degrees of freedom. And only on unimaginably long timescales, far beyond any lab, does complexity bump against its ceiling and start to wander near the top, a saturation that the bulk mirrors as the available interior growth effectively runs out. You can test the spirit of these claims in models simple enough to compute. Chaotic spin chains and random circuits show linear operator growth and late-time plateaus. Holographic toy universes with black holes display interior volumes and patch actions that grow at rates proportional to energy and temperature. When you add controlled disturbances at different times, both sides reveal the same time order sensitivity, with earlier kicks costing more because chaos amplifies them before the undoing begins. Even the role of noise and imperfections maps cleanly. Small errors on the boundary that are easy to correct barely dent complexity, while large, poorly aligned injections push it upward, just as lumps of matter fed to a black hole nudge interior geometry and change the growth rate. None of this proves that complexity is literally equal to volume or action in our universe, and the dictionary is sharpest in highly symmetric, strongly coupled theories where a geometric dual is under good control, but the payoffs are practical as well as philosophical. People who build quantum simulators can read off scrambling rates and circuit depths by measuring simple correlators. Then compare them to bulk predictions to check if their device sits in the same universality class as a gravitational system. Condensed matter theorists borrow the language to understand why certain materials relax slowly, as if trapped on rugged landscapes where reaching equilibrium means climbing through a labyrinth of ever more complicated rearrangements. Computer scientists fascinated by physics gain a bridge from familiar notions, gate counts, circuit depth, algorithmic cost, to exotic ones like interior growth and horizon dynamics. And those of us who like clear mental pictures get a rare gift. A way to say that what looks like empty room behind a horizon may be the geometric face of a computation steadily unfolding, step by lawful step, in the language of the boundary theory. It's tempting to overreach here, so fix two honest boundaries. First, complexity is notoriously hard to define exactly in an interacting quantum field theory, so practical work uses proxies and bounds. And second, bulk measures need careful choices of slices and patches, along with subtractions that remove universal infinities, so the matching is never as trivial as drawing two lines and tilting your head. Despite those caveats, the cross-checks keep accumulating. Shockwave calculations, temperature dependence, energy scaling, sensitivity to the sign and timing of disturbances, and the shared story they tell is consistent. Highly mixed, strongly interacting systems pay for progress not in seconds but in steps, and gravity seems to count those steps with geometric rulers hidden behind horizons. Carry the lesson out gently. When a system feels stuck even as time flows, it may not be idle but busy climbing a staircase of moves that grows steeper as it rises. And when you see a volume swelling or an action accruing in the bulk description, you can read it as a diary of effort, the measure of how much work it would take to recreate, manipulate or rewind the state you have now. In the end, the conjectures are a promise and a provocation. A promise that two distant languages, computation and geometry, are talking about the same underlying labor, and a provocation to test that promise ever more precisely. With better circuits on the boundary and cleaner measures in the bulk, until we know whether the cost of becoming is, quite literally, the shape of the space that becoming creates. Bulk reconstruction from boundary data. You stand at the edge and ask a bold question. If all you can poke and read is the boundary, how much of the hidden interior can you actually rebuild? And the surprising, testable answer is more than you'd guess, but not everything, and only under rules you can learn. In the class of theories where a gravitational world is dual to a non-gravitational one living on the boundary, carefully chosen boundary data, ordinary measurements you can perform at the edge and the way signals bounce when you drive them, contain enough patterns to infer what local fields are doing deep inside, much as a doctor reconstructs a body from X-ray projections, or a seismologist images Earth's mantle from surface rumbles. To feel the mechanism without symbols, imagine you have a repertoire of gentle taps you can apply along the boundary, and an array of microphones that record the echoes as a function of time and location. Then repeat this many times with different tap shapes. By combining all those input-output pairs, you learn a response kernel, a rule that tells you how interior disturbances would have imprinted on the edge. And once you know that rule well enough, you can invert it in a controlled window and solve the inside-out problem. What field value at a chosen interior point would best explain the entire set of boundary readings in simple, curved spacetimes with no horizons to block you? That inversion is almost textbook physics. Smear the boundary data with a neat weighting function over appropriate locations and times, and out pops a good approximation to the bulk field, which you can verify by injecting a tiny test pulse inside and checking that your inversion reproduces it from edge recordings alone. Add a horizon and things become subtler, but not hopeless. You can still reconstruct everything in the interior region that both influences and can be influenced by your boundary patch, a causal wedge. And when you supplement time-ordered drives with more delicate probes of entanglement structure, the reconstructible region often grows into what's called the entanglement wedge, whose boundary is traced by a minimal area surface. The operational meaning is crisp. If that surface wraps around a clump of interior physics, then in principle there exists a recipe, built from boundary observables restricted to your patch, that recovers what happened there. While if the surface leaves it out, no amount of clever post-processing of your patch's data will fully pull the details back. This is not hand-waving, but an algorithmic statement, and you can see its fingerprints in multiple ways. Boundary correlation functions contain characteristic poles and late-time ringings that match the interior's quasi-normal modes, echoes of how perturbations die away behind a curved landscape. And changing the size or shape of your boundary patch causes sharp transitions in which interior points become reconstructible. Just as adding new angles in a CT scan passes a threshold where certain features stop blurring and snap into focus, even the how of reconstruction has diverse faces that agree on the same reality. One route uses explicit smearing over a patch of the boundary's spacetime. Another exploits modular flow, a boundary-only evolution tuned to your specific state that drags interior operators to the edge. And yet another approaches the task like high-fidelity signal recovery, applying a near-optimal inverse map that undoes typical noise and loss to the extent the physics allows. Limitations are as educational as successes. You only get a clean dictionary for interior disturbances that are gentle compared with the local Planck scale, and for states that are not wildly distant from the vacuum. Otherwise, the very notion of a sharp, local bulk field blurs. And when chaos in the boundary has had long times to spread information, the operator you must measure to recover a deep interior event becomes extremely complicated. A practical wall that turns in principle into outrageously hard without contradicting the theory. You also cannot beat causality. The boundary signals you send still take time to influence the interior, and the edge recordings you analyze must wait for the light cone delays that geometry insists on. So any reconstruction protocol comes with a timetable set by distances and curvature, ensuring there is no way to read an event before its causal imprint can reach the boundary. There are sharp diagnostics that show you're doing real interior physics rather than boundary curve fitting. Reconstruct an interior wave packet, and then watch how it reflects from a potential barrier or grazes a horizon. The predicted boundary ringdowns and time of flight delays align across independent reconstruction methods, and if you tweak the curvature slightly, the shift in those delays and the drift of the minimal surface boundary of your reconstructable region match the boundary's shifted response, a triangle of checks that closes. Different boundary teams can also recover complementary interior regions from disjoint patches without inconsistency, with each team's reconstruction agreeing where their wedges overlap and remaining silent where they don't. A division of labor that replaces paradox with a map of who can know what. State dependence, often raised as a worry, is a feature you can learn to handle. The exact dictionary between an interior operator and a boundary observable depends on which global state you are in, because the weightings that invert the kernel shift with the background. But once you commit to a narrow code subspace of states that share the same macroscopic geometry, the reconstruction is stable and can be calibrated by a finite set of edge experiments. Even near horizons where intuition falters, boundary data carry telltale late-time tails whose shapes are fixed by the interior's effective potential, letting you infer, indirectly yet reliably, how close your target sits to the brink. What about the very deep interior or regions flirting with singularities? Here the rules grow cautious. The effective field picture that makes reconstruction meaningful is expected to fail as curvatures approach fundamental scales, and the boundary inversion dutifully signals this by demanding exponentially delicate measurements, or by exploding in sensitivity to noise. A built-in alarm that says, "Your questions exceed the language we agreed to use." The practical moral is generous and usable today, even outside strict holography. If a system has a boundary you can drive and read with high resolution, be it a quantum simulator, a complex material, or a photonic network, then designing tomographic protocols that combine time-resolved responses with knowledge of conserved quantities can let you image interior structures and dynamics that were once thought permanently hidden, complete with honest uncertainty bars that widen exactly where the theory says information bottlenecks lie. Step back and the philosophy lands softly. Bulk reconstruction is not a party trick or a promise of omniscience. It is a disciplined way to turn edge knowledge into interior understanding, constrained by causality, helped by entanglement, and graded by complexity. It teaches you to ask better questions. Which boundary patch suffices? How long must I wait? How robust is the answer to noise? And it rewards those questions with a map whose borders move as you earn the right to know more. In the end, the boundary stops being a wall and becomes a lens. And once you learn how to polish that lens, experimentally and conceptually, you discover that a great deal of what you thought lived only inside was whispering at the edge the whole time, waiting for you to listen in the right way. Firewalls versus smooth horizons debate. You expect the edge of a black hole to be uneventful. That's what decades of general relativity whisper. If you fall through a large, quiet horizon, tidal forces are gentle, and nothing dramatic announces the crossing. Yet a sharp quantum argument seems to demand the opposite, warning that an infaller should hit a searing wall of high-energy quanta, a firewall, and the debate between those two pictures is one of the most revealing stress tests of our ideas about reality. To feel the tension without symbols, hold 4 principles in your hands and notice they don't all fit at once. First, unitarity, the promise that information is never fundamentally lost. Second, no drama, the everyday prediction of relativity that a big, calm horizon feels smooth. Third, local effective field theory outside, meaning ordinary quantum physics should work just outside the horizon. And fourth, monogamy of entanglement, the rule that a quantum bit can't be maximally paired with 2 different partners at once. Now imagine late-time Hawking radiation escaping to infinity and ask what it is entangled with. If unitarity is true, the late radiation must be correlated with the earlier radiation already far away, so that together they can purify into a single, consistent whole. But Hawking's near-horizon calculation also wants each outgoing quantum to be entangled with a partner that falls inward, the gentle pairing that makes the horizon locally look like calm vacuum. The catch is that both can't be true simultaneously for the same quantum. Maximal entanglement can't be split, so either you keep the outside-inside pairing or you break it. This is the AMPS paradox in plain language, and it doesn't go away by hand-waving. From here, the debate branches into concrete options, each giving up or modifying one of the four pillars, and each with testable consequences in principle. You could abandon unitarity, you could deny the no drama and accept firewalls, or you could keep both by weakening local effective field theory right where gravity and quantum mechanics overlap, allowing subtle, state-dependent or non-local effects to reroute the correlations so that late radiation purifies with the early batch, while typical infallers still see a smooth crossing. That last path has grown more persuasive as independent progress has clarified how gravity counts information. The modern island calculations recover the expected page curve, the rise and fall of fine-grained entropy in black hole evaporation, without demanding violent physics at the horizon, by changing the rule for which interior region belongs to the radiation when you compute entropy. So the bookkeeping honors unitarity, while leaving room for gentle horizons for ordinary observers. Does that automatically banish firewalls? Not quite, because the paradox lives in detailed who is entangled with whom stories. So you need to ask a more operational question. Can an observer outside actually distill the delicate correlations from the early radiation, carry them to the whole, and then jump in within a time window that lets them compare the outside partner with the inside partner of the same Hawking quantum to force a contradiction? Several lines of reasoning push that scenario toward the practically impossible. The distillation requires astronomical resources and time that grows wildly with the hole's entropy. The decoding may be computationally intractable long before it's physically forbidden, and attempting it threatens to disturb the very state you need to test, like trying to weigh a snowflake by breathing on it. Other proposals take a more geometric route. Identify the interior partner not as an independent degree of freedom, but as a state-dependent observable, constructed from the same boundary data that also describe the Hawking radiation, so that different observers with access to different wedges of information disagree about which operator represents the mode just behind the horizon, without disagreeing about any shared measurement. This sacrifices a naive, one-size-fits-all dictionary, but preserves both unitarity and smoothness for typical experiences. Alternative, bolder ideas turn the horizon itself into texture rather than emptiness. In the fuzzball picture from string theory, each microstate of a black hole is a horizonless, complicated geometry that only imitates a classical hole from far away, so there is no place for a smooth vacuum at the would-be horizon. In soft hair stories, additional conserved charges living at infinity label states finely enough that information rides out on subtle patterns of radiation. And in Gauss EPR intuition, strong entanglement acts like a non-traversable bridge, suggesting that pairing late radiation with early radiation may be redescribed as a kind of interior connectivity that avoids double-counting degrees of freedom. Each avenue comes with commitments you can probe. State-dependent reconstruction must remain consistent under all operations a feasible observer can perform. Fuzzballs must reproduce the remarkable thermodynamic precision of black hole physics. Soft hair must carry enough capacity to track the ledger of microstates. And any non-local relaxation of field theory must prevent paradox without letting you signal faster than light. Where does the weight of evidence lean today? Hard calculations that include quantum gravitational saddles support unitary evaporation and a page curve without obvious firewalls. Thought-through operational hurdles show that the dramatic distill, dive, and compare experiment is likely out of reach, not just technologically, but in principle for typical black holes. And multiple, independently motivated ideas, error-correcting structures that distribute interior information non-locally, entanglement wedge reconstructions that assign inside data to outside holdings, and complexity-based limits on what observers can actually do, converge on a picture where the horizon stays kind for almost everyone, almost all the time. Honesty still requires room for surprises. Highly engineered setups, exotic microstates, or extreme late-time regimes might produce excitations that an idealized infaller would notice. And the cleanest derivations live in simplified models that capture gravity's rules without reproducing our entire universe. but the upshot you can take with you is practical and calming. Nature seems to keep three promises simultaneously in the regimes we can analyze well. Information is not destroyed. Low-energy observers who mind their own business don't burn up at the edge, and violations of locality, if present, are so delicately arranged that they repair bookkeeping without becoming signaling channels. As you let the noise of the debate fade, a gentler insight remains. Paradoxes arise when we ask for more than one perspective at once, demanding that a single quantum both keep two perfect partners and present the same face to all observers, and the resolution is not to pick a favorite illusion, but to accept that in gravitational worlds, what exists for you depends on what you can actually access and process. Carried that way, Firewall versus Smooth Horizon stops being a horror story and becomes a user's guide to reality's boundaries, reminding you that truth in physics is often conditional, consistent and kind, unitary in the ledger, smooth for the traveler, and carefully stitched so no one can pull on two threads that were never theirs to hold together. Scrambling and the fastest mixers. You learn the difference between losing a message and hiding it in plain sight the first time you watch a quantum system scramble. At the beginning, a tiny, local nudge sits where you put it, but very quickly, its fingerprints spread across the entire system so thoroughly that no simple measurement can find them. And the paradoxical part is that nothing has been destroyed. The information is still there, just braided into correlations that touch almost everything at once. This is what physicists mean by scrambling, and the reason it matters is that it sets the tempo for how complexity and predictability degrade in the real world. From electrons in a strange metal to qubits on a chip to the physics near a black hole's horizon. To develop a working feel for it, imagine lining up many spins or atoms and flipping one by the gentlest amount. If the interactions are short-ranged and ordinary, the disturbance spreads outward like a growing ripple with a finite butterfly speed, carving a cone of influence that expands in time. And inside that cone, simple observables forget where the nudge began, not because energy or particles have finished moving, but because the relationships among many degrees of freedom have changed in a way that simple probes cannot untangle. This is why scrambling is not the same as thermalization. A system can scramble fast, distributing information into global patterns, even while energy currents and densities are still relaxing over longer distances. And conversely, a system can move energy around while remaining poor at weaving information into hard-to-access forms. To measure scrambling without peeking at the answer key, experimentalists use echo-like tricks that compare two nearly identical evolutions, poke, evolve, try to rewind, and then check how much damage the tiny initial poke did to your ability to return to where you started. And the faster that small difference ruins the rewind, the stronger the scrambling. These ideas used to live mainly on blackboards, but now cold atom arrays, trapped ions, and superconducting circuits all run such protocols, effectively sampling out-of-time order correlations that act as accelerometers for chaos, and they reveal rich structure. In clean crystals and chains, the butterfly speed is set by interaction strengths and dimensionality. In systems near localization, the light cone blurs or stalls. In programmable, all-to-all platforms, the spread can be almost instantaneous, reflecting connectivity that ignores geometry. Then comes the audacious benchmark. Among all thermal quantum systems respecting basic rules of cause and effect, there is a universal upper limit to how fast chaos can grow, tied directly to temperature, and while most materials fall comfortably below it, gravity in its most extreme, black hole guise appears to meet that limit, making such horizons the fastest mixers allowed by nature. That statement is less mystical than it sounds. Near a horizon, the redshift and density of states conspire to amplify tiny differences at the maximum lawful rate, turning the region into a kind of perfect blender for information, so that from the outside, any simple attempt to read what fell in is quickly drowned by the tide of correlations. The idea of a fast scrambler sharpened an older puzzle into a crisp test. If you toss a diary into a large, hot black hole, how long before the outgoing radiation contains enough scrambled traces that, in principle, an observer who already held past emissions could begin to reconstruct the message? The modern answer says, The waiting time grows only with the log of the black hole's entropy, astonishingly short compared with the time it takes to emit everything, which is why black holes have become the paradigmatic laboratories for scrambling. Not because we can run those experiments in space, but because the same logic guides what we do in the lab on small, clean systems. The practical consequences are immediate. In quantum processors, scrambling is a double-edged sword. Too little, and your device remains simple but brittle. Too much, and errors diffuse into patterns that are hard to correct, unless you have matching redundancy. So engineers tune interactions and scheduling to manage the growth of operator size. The technical way of saying, how many parts does a simple poke eventually touch? Material scientists exploit the distinction between scrambling and transport to diagnose strange conductors, where charge may move sluggishly while quantum information races, or vice versa. And theorists use scrambling as a ruler for phases of matter that look identical thermodynamically, but differ in how quickly they hide local secrets. A subtlety worth keeping at the center is that fastest is not an insult but a property. Reaching the upper limit does not break any rule. It saturates one, and systems that do so often provide clean, universal behavior. Their echo decay has a characteristic slope set by temperature. Their butterfly fronts propagate with a well-defined velocity tied to microscopic couplings, and their response to carefully timed kicks displays telltale switchbacks and plateaus that match analytical predictions. At the same time, constraints keep the story honest. Causality forbids influences from outrunning the system's own maximum signal speed, so the butterfly cone cannot expand faster than those microscopic limits. Conservation laws can slow or reshape the cone. Disorder and interference can fragment it. And in extremes like many-body localization, scrambling may halt, preserving local memory far longer than naive intuition allows. Bridging to the broader narrative, scrambling also reframes recoverability in clear, testable terms. If a disturbance has spread to touch a finite fraction of the system, then the operator needed to reverse it becomes correspondingly complex, something like a surgical rewrite of many degrees of freedom at once. Which is why the line between in principle we could unscramble and in practice we never will is drawn not by physics alone, but by computational cost. This recognition lifts paradoxes into engineering questions. You no longer argue about whether information is lost. You ask what resources and timescales are required to retrieve it, and those answers often come back with exponential price tags. As you let the idea settle, the human-scale lesson is unexpectedly gentle. Scrambling is not a synonym for chaos or ruin. It is the universe's way of protecting detail by diluting it across the whole, and learning the tempo of that dilution, how fast, how far, and under which constraints, turns into a practical skill whether you are building a fault-tolerant quantum chip, imaging hidden structure in a complex medium, or interpreting signals from a strongly interacting material. And when you return to the beginning image, the single flip dissolving into a sea of relations, you can see why black holes became the parable of fastest mixers. Not because they swallow truth, but because they force you to refine what accessible truth means, reminding you that in a lawful world, the most delicate answers are rarely erased, merely woven so widely that only the right questions, asked with patience and precision, can coax them back into view. Out-of-time order correlators explained. You learn what it means for a tiny cause to become a global effect the first time you meet an out-of-time order correlator. Not as an equation, but as a carefully staged experiment that asks, if I nudge a system here and now, how much will that ruin my ability to undo the past later? And then listens for the answer. The protocol feels like a magic trick with all the mirrors removed. Prepare your system, give it a small local poke, let it evolve forward, attempt a partial rewind, and finally check whether a simple measurement that used to return a crisp value now comes back blurred. And the degree of that blur is the OTOC. It quantifies how a microscopic change spreads into the many degrees of freedom so thoroughly that even a best effort echo can't cleanly refocus. The key is the strange time ordering baked into the name. You don't just measure before then after. You deliberately interleave operations from different moments so that the test is sensitive to the system's habit of amplifying differences, the quantum analog of the butterfly effect. In a calm, integrable world where motions are coordinated, that amplification is mild. The OTOC stays near its initial value for a long while, and your echo works. In a chaotic, strongly interacting world, small disturbances grow into complicated operators that touch many parts at once. The OTOC decays on a characteristic timescale, and even a perfect rewind routine can't restore what a local nudge has smeared across the whole. This makes OTOCs the right yardstick for scrambling rather than mere energy flow. They measure how quickly, who influences whom, becomes a dense web, not how fast heat diffuses. And that distinction explains why some conductors shuffle charge slowly while their OTOCs fall fast, or vice versa. Laboratories now extract OTOCs without ever writing the underlying formula on a board. Trapped ion arrays toggle between forward and backward evolutions and watch an interference fringe fade. Cold atom experiments imprint a tiny phase twist, run time forward, reverse the sign of interactions using control fields, and compare the refocusing quality. Superconducting circuits send a probe into a small processor, perform a controlled near rewind, and read out a contrast that maps to the OTOC. Even randomized measurement techniques, scrambling the initial state in many ways and averaging, recover the same decay curve while tolerating more noise. Each platform confirms the same story with different weaknesses. Finite size produces revivals that ride on top of the decay. Imperfect time reversal makes the tail look heavier than it should. And classical noise can mimic chaos, unless you separate its signature from genuine operator growth by varying temperature, interaction range, and the geometry of couplings. The physics encoded in the early time slope and the light cone shape of the OTOC is especially revealing. There is a speed limit for how fast a butterfly front can move through a system, set by its microscopic couplings and dimensionality, and a separate growth rate that tells you how quickly nearby influences become effectively independent. Generic many-body systems respect both limits, while the most extreme mixers, black hole-like models used in theory as chaos benchmarks, push the growth rate up to a universal ceiling proportional to temperature, an observation that connects a tabletop echo experiment to some of gravity's most exotic predictions. On the flip side, when disorder pins motion into many-body localization, OTOCs refuse to fall in the usual way, growing only very slowly or not at all, preserving local memory even though time passes. A crisp diagnostic that you are in a phase where information resists dilution. Practical payoffs are immediate. Device builders use OTOCs to score quantum processors, not just on gate fidelity, but on their dynamical character. How rapidly small programming errors spread into global ones, which informs error correction schedules and the placement of checkpoints. Materials researchers compare OTOC cones with charge and heat cones to label unfamiliar regimes in strange metals where conventional transport laws fail. And control theorists tune interactions to shape OTOC decay on demand, making systems that scramble only after a design delay or that confine growth to chosen subspaces. Useful when you want rich dynamics without losing handle on them. It's also clarifying to separate OTOCs from lookalike probes. A Loschmidt echo tests your ability to reverse dynamics after a small, global imperfection and can be fooled by noise you didn't intend, whereas an OTOC is built to spotlight the local butterfly. Flip a spin here, attempt to rewind there, and ask how badly the flip spoils the distant measurement. So it focuses on operator growth rather than generic fragility. Caution keeps the tool honest. OTOCs are exquisitely sensitive and therefore hard to measure deep into their decay, where any tiny calibration error or leakage channel can masquerade as genuine chaos. So the best experiments vary the probe size, change the location of the initial nudge, and check scaling with system size to make sure the extracted rates and velocities obey causal bounds and conservation law constraints. Taken together, the method turns a philosophical idea, small causes, big effects, into a stopwatch and a ruler you can use in the lab, with a decay curve that times how quickly a system hides local detail and a spreading front that maps how far that detail has reached. And when you let the idea settle, a gentle lesson remains for how to think about complex worlds beyond physics. Sometimes the measure of resilience is not whether you can rewind exactly, but how fast small mistakes become everyone's problem. And OTOCs give you a way to see that tempo clearly, to design systems that endure it, and to accept that in healthy complexity, the most delicate facts aren't destroyed. They are simply woven so widely that only careful, out-of-time questions can find their way back. SYK models, chaos and gravity toys. You don't expect a handful of randomly interacting particles to teach you about the edge of a black hole, yet that is exactly the promise of the Sachdev-Yekitayev family of models. Take many simple constituents. Think of them as tiny fermionic switches. Wire every switch to every other, with strengths drawn from a lottery, and let the whole thing evolve. And out of that unruly start emerges a system you can solve in the limit of many switches. One that behaves at low energies as if time itself has become elastic and chaos has reached its lawful maximum. The construction is plain enough to describe without symbols. You have a large box of microscopic degrees of freedom. You connect any 4 of them at a time with a random coupling, and you average over that randomness to focus on universal patterns rather than the quirks of a specific wiring. In that large box limit, a miracle of simplicity appears. The messy high energy, details wash out, and the 2-point memory of the system settles into a universal form, controlled by an approximate symmetry that stretches and relabels time. A reparametrization invariance, gently breaking that symmetry, leaves behind a single soft mode whose dynamics are governed by a remarkably compact rule. And that soft mode sets the system's low temperature thermodynamics. Specific heat grows linearly, with temperature like a strange metal. There's an unusually large density of low energy states, and even at very low temperatures, the model remembers a finite amount of microscopic disorder as a residual entropy in the infinite size idealization. Chaos in this playground is not a metaphor but a measurable pace. If you track how a tiny, local tweak becomes a sprawling many-body influence, you find the earliest growth rate saturates a universal ceiling proportional to temperature, the same bound that near-horizon gravity seems to meet, which is why SYK became the benchmark for fast scramblers. But its value goes beyond a fast rate. You can compute the full time and temperature dependence of the 4-point echoes that diagnose scrambling, watch ladder-like corrections build the decay profile, and see in the spectrum the fingerprint of quantum chaos known from random matrix theory. Short spacings repel. Long scales display a ramp and plateau pattern when you process the energy levels into a spectral form factor. And that ramp shows up at the right timescale to signal when individual energy levels start talking to each other statistically. Because the model is solvable, you can connect these moving parts with clean logic. At high energies, the interactions look nearly featureless. At intermediate scales, the reparametrization mode dominates. And at late times, the discreteness of the spectrum, the fact that you don't have a continuum, enforces a universal saturation of fluctuations. The bridge to gravity is not hand-waving, but a concrete dictionary in a special corner of spacetime, where the bulk looks effectively two-dimensional near a horizon. There, the same soft time relabeling shows up as a simple theory of boundary motion coupled to a patch of curved interior. And the low-energy rules that govern SYK's correlators match those that govern the boundary of that gravitational toy world. From that vantage point, interior growth, horizon response, and even delicate questions about how 2 copies of a system share information acquire a geometric flavor. And conversely, abstract gravitational ideas are translated into operational lab recipes. How to kick, how to read, how to time a probe, without leaving the safety of a many-body Hamiltonian you can simulate. The playground is richer than the original box. Variants with charged fermions let you study transport and strange metallicity. Supersymmetric cousins sharpen the symmetry story, and tensor models remove the literal randomness by engineering interactions whose combinatorics mimic the same solvable large-size limit, proving that the universality is not a fluke of disorder, but a feature of a broad class of strongly interacting designs. Critics sometimes worry that random interactions sound unphysical, but condensed matter proposals have chased SYK-like behavior in real platforms. Quantum dots coupled through superconductors, arrays of Majorana modes engineered in nanowire networks, twisted graphene devices with enhanced interactions, and even programmable quantum processors, where effective all-to-all couplings can be dialed in, and they look for telltales. a tunneling conductance that scales with temperature with non-Fermi liquid exponents, an entropy that refuses to vanish as quickly as in a standard metal, or an echo experiment whose early time decay hugs the chaos bound. Another worry is whether averaging over disorder hides individual quirks you'd actually care about in a single sample. And here the model is kind. For large enough boxes, a single messy instance tends to mimic the average, a property called self-averaging. So the universal predictions survive the move from ensemble to device. Perhaps the most counterintuitive payoff is conceptual. Because SYK is soluble and yet maximally chaotic, it sits at a sweet spot where you can test ideas about complexity growth, information recovery, and even wormhole-like protocols in a setting that does not assume geometry from the start, letting geometry reappear as the most economical language for what the many-body system is already doing. That reappearance carries practical consequences. The soft mode that rules low energies also controls how sensitive the system is to timing errors in control pulses, which matters if you want to use the model as a scrambler in a quantum circuit. The same spectral universality that gives you a ramp also tells you which imperfections will smear it out first, a guide for experimental design. And the fact that two coupled SYK boxes can enter phases where their low energy states act like a single, gently connected object gives you a way to practice teleportation with chaos protocols, where fragile information is routed rather than lost. None of this claims that the universe is an SYK box, and you should keep the humility that comes with any toy. It lives in one dimension, ignores spatial structure, and idolizes disorder. Yet for teaching the grammar of strong interaction, how solvability can coexist with maximal chaos, how thermodynamics emerges from a single soft degree of freedom, how gravitational intuition and quantum control talk to each other, it is hard to find a better blackboard. The quiet lesson as you step away is that randomness, used wisely, is not the enemy of meaning, but a solvent for irrelevancies. Strip a complex world down to couplings that look statistically featureless, and what refuses to wash away, the soft symmetries, the chaos ceiling, the spectral fingerprints, are the parts of the story likely to be true far beyond the toy, including at the edges of gravity where we learn to listen for them first. Spin networks in loop quantum gravity. You've spent your life treating space like a smooth stage, but loop quantum gravity asks you to imagine the stage as a scaffold of tiny links and junctions, spin networks, where geometry is not drawn first and filled later, but assembled from the start by combinatorics. And the surprise is how far you can go with that picture without writing a single symbol. Take a graph. Let each edge carry a quantum of twist, and let each node enforce a quiet balance rule that glues the twists consistently. And suddenly the edges behave like indivisible strands of area, while the nodes behave like grains of volume. In this view, the metric, the ruler you normally use to tell what is long or short, doesn't exist independently. It is reconstructed from the pattern of labels on the graph, so that a triangle of connections with small labels computes to a tiny patch of area, and a node with higher capacity couplings computes to a chunk of volume. And because those labels change in discrete steps, area and volume come out in discrete spectra rather than continuous smears. This is not a metaphor layered on top of classical space. It replaces classical space in the deep regime with a background-free kinematics. There is no pre-drawn grid hiding behind the graph. Only the graph itself, so motion, curvature, and distance are all summaries of how the network is wired and how its labels update. If you want a tactile analogy, think of a city at night seen from far above. Smooth roads by day dissolve into a lattice of lights, and yet, from that lattice, you can still read neighborhoods, avenues, and rings around the center. Coarse-grain the pattern and a smooth map reappears. Spin networks promise the same reconciliation. On the Planck scale, the world is granular and relational, but when you coarse-grain many edges and nodes into superlinks and superjunctions, a metric with familiar properties emerges, a weave that approximates smooth geometry with controllable error. The raw ingredients are humble. Loops, or more precisely holonomies, traces of how a test arrow rotates as you drag it around a closed path, become the basic variables, and the quantum states built from them arrange naturally into graphs whose edges carry representations of the underlying symmetry and whose nodes carry intertwiners that ensure the flows match. The result is a Hilbert space spanned by these graphs, and every state is a superposition of different graphs with different labels, like a choir of possible microgeometries singing together to produce the macrogeometry you measure. Dynamics, of course, is where skepticism lives, and loop gravity's answer is to let spin networks evolve into spin foams, histories where edges sweep out faces and nodes sweep out volumes in a higher dimensional mosaic, and transition rules assign amplitudes to local moves that split, merge, or reroute the graph. Because the theory never leans on a fixed background metric, the evolution is designed to be diffeomorphism invariant from the start. The symmetry that, in general relativity, says coordinates have no physical meaning, now lives as the freedom to redraw the graph without changing the physics. And that is why enthusiasts call the approach background independent with pride. You can test whether this scaffolding reproduces known landmarks, count the microstates of a black hole horizon by letting spin network edges puncture a spherical surface, and tally the ways their labels can add up to the same macroscopic area, and you obtain an entropy proportional to the area with a coefficient that can be matched by fixing a single quantization constant, an encouraging echo of the famous area law. Ask whether the early universe can avoid a singular start. And simplified cousins of the theory, loop quantum cosmology, replace the Big Bang with a bounce once densities approach the fundamental grain size, turning a fatal divergence into a reversible compression, where the discrete nature of geometry creates a repulsive pressure that halts collapse. The fair, sober part is that these are still models and extrapolations. We don't yet have a decisive experiment that singles out the spin network picture, and rival approaches tell their own compelling stories. But the spin network language pays dividends even before such an experiment arrives. It teaches you to separate what geometry means from any particular coordinate picture, and it gives you a practical algorithm for building space from relations rather than declaring it given. It also dovetails with tools you may already know from quantum information. A spin network is a special kind of entangled graph state whose constraints at the nodes mirror conservation rules. And coarse graining, it resembles renormalization on lattices, where you summarize many small links by a few effective ones without losing their large-scale influence. You can test consistency by seeing how semi-classical states, broad, superpositions tuned to peak around a smooth geometry, propagate under the graph's update rules, and whether small ripples behave like gravitons in the right limit. And although deriving full Einstein dynamics in a clean, closed form remains the holy grail, partial checks in low curvature regimes and specific spin foam models keep landing in the right neighborhood. Phenomenology keeps a cautious, creative list of maybe signatures. Tiny, energy-dependent delays in high-energy photons sent across astronomical distances, imprints in polarization patterns of the cosmic microwave background, or subtle modifications of black hole ringdowns. But every honest review will tell you these searches are hard and noisy, and the theory's predictions must be sharpened to avoid mistaking astrophysical clutter for quantum gravity whispers. Still, as a way to think, and to teach yourself what quantum spacetime could mean, spin networks are unusually concrete. You can sketch a handful of nodes on a page, assign labels, compute elementary area and volume quanta, and watch how simple local moves reshuffle geometry without appealing to an invisible continuum. The conceptual gift at the end is gentle but firm. Rather than a world that has space and then populates it with matter, you get a world where matter and the connections among fundamental degrees of freedom are what space is, and smoothness is the large number illusion that your senses mistake for bedrock. If you sit with that long enough, the message becomes less radical and more practical. You don't need to know the smallest bricks to trust the house. But knowing that bricks exist explains why the house can resist infinite pressures, avoid impossible infinities, and still look, from across the street, like a single seamless wall, discrete area and volume spectra. You're used to thinking of area and volume as smooth. Stretch a surface a little, its area changes a little. Squeeze a region softly, its volume shrinks softly. but a quantum view of geometry whispers a different rhythm. At the tiniest scales, the amount of surface and the amount of bulk do not slide continuously. They come in discrete notes, like steps on a well-made staircase that are too small to notice from afar, but impossible to ignore up close. And this idea of discrete area and volume spectra carries crisp, testable meaning without any heavy symbols. The simplest way to feel it is operational. Imagine measuring an area not by laying a ruler, but by bouncing a quantum probe. Light, atoms, anything you can count, off a boundary, and asking what outcomes recur. In a world truly continuous to the bottom, there is no preferred set of outcomes, only ever finer subdivisions. In a quantum geometric world, however, there is a lowest non-zero tick of area, and a ladder of higher ticks determined by how the underlying microstructure of space can arrange itself, and the same for volume, with tiny grains that add up in specific combinations rather than blending. One concrete construction that realizes this picture turns geometry into a network of relationships and shows that when you ask, what is the area pierced by these strands, or what is the volume enclosed by these junctions, the answers land on discrete sets. No matter how you tweak the calculation, you do not get a continuum, you get a spectrum. Crucially, this is not an arbitrary discretization imposed by hand. It's the consequence of treating geometry itself as quantum, with observables that cannot be sharp and continuous simultaneously, any more than position and momentum can be in ordinary quantum mechanics. That discreteness is not merely cute. It addresses old headaches head-on. When your theory tries to push curvature or density to infinity, the discrete steps act like ribs that resist further compression, cutting off the otherwise unstoppable growth of how much stuff per unit area or volume, and replacing catastrophic singularities with regimes where the building blocks of space push back. You see this most vividly in simplified cosmological models where the classical picture predicts a beginning with zero volume and infinite curvature, while the quantum geometric version replaces that point with a bounce at a finite, minimum volume set by the grain size, turning never into not allowed by the microstructure. On black hole horizons too, discreteness earns its keep. If edges of the underlying geometry puncture a surface, they contribute area in quantized chunks, and counting the ways those chunks can sum to the same macroscopic area reproduces the famous entropy area law, with a single free constant fixed by matching the coefficient. An echo of how atomic theory once explained thermal properties of gases by counting invisible bits. Yet discreteness does not mean jaggedness to the naked eye, because quantum states of geometry can superpose many nearby eigenvalues to create a weave whose averaged, coarse view is as smooth as any classical metric you've ever drawn, just as a digital photo looks continuous, from a distance even though it is pixels up close. So you retain all the practical continuity needed for everyday physics and for the majestic curvature of general relativity at large scales. Skeptics often ask whether a smallest area or volume would clash with the principle that no inertial observer is special. But the resolution is familiar from quantum theory. The spectrum is a statement about what you can measure, not about a lattice nailed into a preferred frame, and the machinery that defines these observables is built to respect the freedom to relabel coordinates. So there's no hidden grid rushing past you. More subtly, discreteness here is kinematic. It tells you the allowed outcomes of measuring geometry, while dynamics is encoded in how these outcomes update when matter moves and fields interact. One can visualize the history of the discrete scaffolding as a foam of evolving faces and volumes, where local moves change the labels in tiny bursts, and the large-scale effect of many moves averaged together recreates smooth curvature and gravitational waves, restoring classical predictions where they are known to work. Could you ever see the discrete steps directly? Not by counting Planck-scale squares with a magnifying glass, those scales are beyond our current reach, but by looking for their integrated consequences. Ultra-energetic photons from distant explosions might accumulate a minuscule, energy-dependent delay on their way to us if the microstructure imprints a universal correction. Polarization patterns in the cosmic microwave background might carry traces of early universe dynamics where the minimum volume prevented naive singular behavior, Ringdowns of newly formed black holes could, in optimistic scenarios, include faint echoes if the near-horizon structure departs from the pure classical continuum, and precision interferometers on Earth continue to tighten constraints on any would-be graininess in how paths compare, even if these searches stay quiet for a while, as caution suggests they might. The discrete spectra picture is already useful as a conceptual and computational tool. It regularizes integrals that would otherwise blow up. It organizes the bookkeeping of quantum states of geometry into countable chunks, and it provides a clear target for semi-classical states that aim to mimic smooth space with quantifiable errors. There are honest caveats you should carry with the same care as the promise. Different formulations can yield different detailed ladders of allowed values, and a constant that calibrates the size of the steps must be fixed by a physical match the way Planck fixed his when quantizing light. The cleanest derivations live in idealized settings where symmetry keeps the math transparent, and stitching those results into the full messy universe is ongoing work. Moreover, quantum measurements broaden sharp lines. No experiment will give you a needle-thin spike at a single eigenvalue, but a distribution peaked around it. So the phenomenology is about small, systematic shifts and quantized tendencies rather than cartoon-like pixel edges in the sky. Still, the long view is steadier than the caveats. Whenever physics has discovered discreteness, atoms of matter, quanta of light, energy levels of electrons, confusion has turned into clarity, infinities have yielded to finite counts, and practical calculations have gained a trustworthy backbone. Discrete area and volume spectra propose the same kind of pivot for spacetime, suggesting that the solidity of the world is not a continuous block of marble, but a masterful mosaic whose tiles are too fine for our senses, yet just rigid enough to keep the universe from tearing where classical ideas would fail. Let that thought close softly. The next time you run a hand across a table or gaze at a horizon, you can still trust the smoothness you feel and see. But somewhere beneath that ease, the world may be ticking in tiny geometric quanta, a discipline of steps that keeps the grand dance of curvature and motion in time. Causal sets. Order before geometry. You're used to drawing space first and then letting causes flow across it. But the causal set idea flips the order. Start with nothing but a list of who can influence whom, a bare partial order of events. And promise not to add anything else, no grid, no coordinates, no background, then show that geometry can be rebuilt from that order and simple counting. So that distance, dimension, and even curvature become summaries of causal relations. The rules are Spartan and clear enough to feel. Every fundamental element is an elementary event. Some events can be ancestors of others, meaning a signal could go from the first to the second at or below light speed. Many pairs are unrelated, no influence either way, and the set is locally finite so that between any two related events, there are only finitely many intermediates. If you draw a Hasse diagram, dots for events, arrows for immediate can-effect links, you get a skeletal universe where the arrows encode the light cone structure and the sheer number of dots in a region encodes its volume. And from only these two ingredients order, plus counting, you can, in principle, reconstruct the continuum geometry that would approximate the set at large scales. This reversal isn't wishful thinking. Precise theorems in continuum physics say that in an ordinary spacetime, the causal order already pins down its shape up to local rescaling, and volume fixes that last ambiguity. So if your discrete order approximates the right continuum order, and your counting matches volumes on average, you have enough information to recover distances and curvatures at scales large compared with the grain. Operationally, it becomes a puzzle you can solve without equations. The longest chain of related events between A and B estimates the proper time between them. More steps mean more time. The size of the largest unrelated anti-chain that fits between two moments behaves like the cross-sectional area of a space-like slice. And quick dimension estimators ask how the number of relations scales with the number of elements in a neighborhood to infer whether you're living in something like 2D, 3D, or 4D. To keep faith with relativity's no preferred frame, you don't sprinkle events on a rigid lattice, which would pick a rest system. You rain them randomly with a Poisson process, so that different observers see statistically the same pattern. Every region gets, on average, a number of events proportional to its volume, but with random fluctuations that blur any would-be grid lines, so Lorentz symmetry survives in the only way a discrete theory can let it survive. Not exactly at the tick-by-tick level, but exactly in the statistics. Then you can ask dynamics. The hard question, how does the order grow? One natural answer imagines the universe accreting new events one by one in a way that respects causal precedence. So an event can only sprout from a past that already exists, while modest principles, no way to label the births after the fact, discrete general covariance, and no influence, that jumps outside past light cones, narrow the allowed growth laws to a family you can actually simulate, producing webs with long chains that look like world lines and wide layers that look like spatial slices. To compute with such a world, you need discrete versions of continuum tools. A retarded non-local D'Alembertian that acts on fields by sampling a thickening of the causal past, thick enough to smooth out graininess, but thin enough to be faithful. Curvature estimators that read the excess or deficit of small order intervals the way a surveyor reads triangles. And an action, the thing you extremize to get equations of motion, built from counts of tiny motifs in the order. Remarkably, when you coarse-grain big, well-behaved causal sets, those discrete constructions reproduce familiar continuum behavior, while near the grain scale they soften the infinities that plague classical gravity. The approach has a distinctive phenomenology portfolio that's cautious rather than sensational. Because sprinkling respects Lorentz symmetry statistically, you don't get obvious preferred frame effects. But Poisson fluctuations in element counts could, over cosmological volumes, behave like a tiny, ever so jittery vacuum term whose average is small but whose variance doesn't entirely vanish, suggesting one path, among many being explored, to a small effective cosmic acceleration. On the particle side, the same non-local retarded operators predict ultra-weak swerves, a diffusion-like, broadening in momentum space that is bounded by high-precision observations, so far consistent with zero but a concrete target for improved measurements. Black hole horizons can be described as order-theoretic cuts, and counting how links cross a horizon offers an order. First way to revisit the entropy-area relation without assuming a smooth surface to begin with. None of this says the story is finished, turning growth rules into a full quantum dynamics, proving that typical histories look manifold-like at large scales, and nailing unique numerical coefficients remain open and lively problems. But the conceptual payoffs are already instructive. It becomes obvious why geometry should be relational if cause is primary. It becomes clear how discreteness can coexist with relativity without violating it. And it becomes natural that volumes, times, and even curvature should be read from statistics over events rather than from a presupposed grid. Perhaps the most surprising lesson to carry away is practical humility. If all you truly know are the precedences, who could have influenced whom, then the smooth map you like to draw is not a background you live in, but a summary of that order, a large number mirage that works because the universe is big and busy. In that light, the Big Bang singularity looks less like a place where equations fail, and more like a warning that you've pushed the continuum summary past its domain, and the fix is not to add epicicles to a metric, but to return to the only data that never lied, the partial order of events and the finite counts between them. Let the thought close softly. You can still use rulers and clocks because, for you, the world is large enough to average over the grain. But beneath that ease may sit a universe that doesn't keep a coordinate book at all, only a ledger of causation, from which the distances you trust and the spaces you walk through are written after the fact. Group field theory and emergence. You don't begin with space at all. You begin with ingredients that don't look like space, a handful of abstract atoms of geometry labeled not by positions but by group theory data. And group field theory asks you to watch what happens when vast numbers of these atoms interact and condense. The way molecules in a vapor can suddenly organize into a liquid with waves, currents, and sound. The move is radical yet concrete. Instead of drawing a continuum and quantizing ripples on top, you define a quantum field whose arguments live on a compact group. Think of the symmetries that describe how little triangles or tetrahedra can be rotated and glued, and a single quantum excitation of that field is interpreted as a tiny building block of space, an oriented simplex with algebraic labels that carry area and angle-like information. You then allow these quanta to meet at their faces according to interaction rules that enforce consistency of gluing, and the diagrams that track their interactions. Feynman diagrams in this algebraic world add up to histories of discrete geometries, the very same combinatorial foams that appear in other non-perturbative approaches to gravity. The philosophical turn comes next. Rather than declaring any single discrete geometry to be the world, you consider many body states with huge numbers of these quanta and study their collective phases, asking whether there exists a regime where expectation values behave like a smooth metric and long wavelength excitations look like gravitational waves. This is where emergence enters with teeth, not poetry. Coarse graining techniques borrowed from statistical physics let you integrate out microscopic details. Renormalization teaches you how interaction strengths flow as you zoom out, and you map the theory's parameter space to see whether there are fixed points that signal robust macroscopic behavior independent of microscopic quirks. One particularly evocative class of states are condensates, coherent collections of quanta all populated in the same microscopic configuration. And when you write down the effective equations that govern these condensates, equations that play the role of hydrodynamics for the pre-geometric fluid, you find versions of cosmological dynamics, a total density of quanta that grows or shrinks with an internal clock, an effective scale factor that obeys Friedman-like relations with quantum corrections, and in many scenarios a bounce at high density that replaces the classical singularity with a reversible, finite minimum, a pattern that echoes what you'd expect when discreteness resists infinite compression. What is striking is that these cosmology equations are not put in by hand as a wish list. They emerge from expectation values of the fundamental group-valued fields under mild assumptions about symmetry, and from the simplest interaction kernels that glue, building blocks into larger wholes. If you perturb a condensate, ripples in occupation number, small mismatches in the group labels, you can derive linearized dynamics for these inhomogeneities and ask how they would appear as scalar or tensor fluctuations on the resulting emergent spacetime, bringing the program to the doorstep of early universe phenomenology. One can, in principle, look for fingerprints in the cosmic microwave background, or in the statistics of primordial gravitational waves that would gently deviate from the predictions of a purely classical beginning. None of this requires you to abandon the appealing virtues of background independence because there was never a background to begin with. The only where that exists is the relational data encoded in how quanta glue along their faces, and continuum coordinates arise only as macroscopic charts that summarize those relations once the system condenses into a phase with smooth behavior. The architecture is richer than a single model. Choose different groups, compact ones related to spatial rotations, larger ones that encode boosts. Choose different valences, triangles, tetrahedra, higher dimensional polytopes. Adjust the combinatorics of interactions, which faces meet which, and you scan a family of theories whose continuum limits can share the same universal physics if they flow to a common fixed point, just as water can be described by different molecular models but shares a phase, diagram with liquid, gas, and critical points. In this light, geometrogenesis, the idea that the universe underwent a phase transition from a pre-geometric phase to a geometric phase, stops being rhetoric and becomes a calculable possibility. Above a critical temperature, or below a critical density of quanta, no smooth description exists, correlations are short-ranged, and talk of distances is meaningless. Cross the critical surface, correlations blow up, a condensate forms, and a metric becomes the correct language for long-wavelength observers like us. You can even sketch experimental footholds. If the early universe passed through such a transition, it could seed specific non-Gaussian imprints or leave small, scale-dependent shifts in the spectrum of primordial perturbations. And if black holes probe densities where the condensate picture breaks down, Late-time ringdowns might include tiny departures from classical expectations, subtle, to be sure, and hard to isolate, but qualitatively distinct from mere astrophysical noise. The strengths of group field theory are matched by honest challenges, deriving full general relativity with all its local gauge structure and constraints, as the unique hydrodynamic limit is ongoing work. Ensuring exact local Lorentz symmetry at low energies requires careful control over how boost symmetries emerge from compact building blocks, coupling matter consistently, deriving familiar particle fields as excitations, or defects of the same pre-geometric medium rather than appending them by hand, is an active frontier where promising toy constructions exist but a seamless, standard model remains distant. Uniqueness questions persist too. Several interaction kernels and combinatorics can produce similar macroscopic behavior, so the theory must either predict why our world selected a specific microdynamics, or demonstrate that universality renders the choice irrelevant for all observables we can measure. Even with those caveats, the computational loop has begun to close. Renormalization group studies identify regions of parameter space where the theory is asymptotically safe or at least well-behaved. Tensor model cousins, stripped-down versions that keep the combinatorics and ditch some group structure, confirm that large N expansions can be controlled and that certain melonic diagrams dominate, simplifying the path to continuum behavior. And cross-pollination with canonical loop quantum gravity aligns the microinterpretation of quanta with spin network labels, making sure that the quanta you count in the field theory really are the bits of area and volume that other approaches quantize. Perhaps the most productive way to hold the picture is to borrow an intuition from condensed matter without importing its limits. A superfluid is not a collection of little water blocks, yet we can model it with field operators acting on a Fock space of atoms and recover sound, vortices, and flow. Likewise, group field theory is not a Lego kit of literal triangles, but a quantum many-body theory whose quanta, constrained by group symmetries, assemble into states whose large-scale, long-time behavior deserves to be called spacetime. Asked what this buys you, the answer is clarity about questions you can actually pose. How many quanta per horizon-sized region does an emergent universe contain at a given epoch? How do perturbations in that number propagate during a bounce? What interaction strengths keep the condensate stable against fragmentation? Which renormalization trajectories deliver semi-classical behavior over the largest dynamic range? In each case, the knobs and dials are explicit, and the predictions, while still rough, have the virtue of being falsifiable in principle. Let the idea settle with a gentle shift in perspective. Instead of searching for a final equation written directly for the metric, you attend to the pre-metric choir and ask under what conditions their collective song stabilizes into the symphony we call geometry. In that posture, emergence is not a downgrade of reality, but an upgrade of explanation, taking you from an assumed backdrop to a world in which the stage, the actors, and the script coalesce from the same microscopic score, and reminding you that the most durable structures in physics, fluids, crystals, magnets, and perhaps spacetime itself, are less about the bricks they are made of and more about the patterns those bricks agree to play. Asymptotic safety, taming gravity's UV. You've heard that gravity misbehaves at the smallest distances, that when you push Einstein's elegant equations into the ultraviolet, toward ever higher energies, ever shorter scales, the usual tools of quantum field theory drown you in infinities. Yet the asymptotic safety program asks you to pause, breathe, and try a different question. Instead of demanding that every coupling constant stay small as you zoom in, ask whether the whole flow of couplings under coarse graining might settle into a stable pattern, a fixed point that tames the wildness without requiring gravity to be weak. To make that concrete without symbols, picture physics as a map with a zoom slider. Slide down and you average over small ripples. Slide up and you resolve finer structures. The rules that tell you how the strengths of interactions change with zoom, the renormalization group, can act like trade winds on this map, pushing you toward particular regions no matter where you start. And an ultraviolet fixed point is a harbor in the high energy corner, where the winds die to a constant direction, so your ship stops being blown into nonsense. If such a harbor exists for gravity, then as you probe ever shorter distances, the effective Newton coupling and its companions do not explode, but approach steady values or steady scalings, and the theory remains predictive, because only a finite number of directions in the giant space of possible interactions actually matter for long-distance outcomes. The rest are washed away as you flow into the fixed point. That is the safety in asymptotic safety. Not safety by smallness, but safety by stability. The case for this rests on a blend of rigorous logic and dogged calculation. Decades of work with non-perturbative tools, especially a technique called the functional renormalization group, which evolves an effective action as you adjust a resolution scale, have tracked how candidate gravitational couplings run together. When you truncate this infinite bookkeeping to a manageable subset, keeping, say, curvature terms up to a certain complexity, you repeatedly find a non-trivial fixed point that pulls the flow in the ultraviolet, with only a handful of relevant directions, knobs you must set by experiment, while all other details are irrelevant in the technical sense and get ironed out. This picture survives when you complicate the truncation by adding higher-order curvature terms, when you couple simple kinds of matter, and when you vary the technical scheme used to regulate short-distance modes, which suggests you are not seeing an artifact of a particular approximation, but a robust feature. Along the way, the running of the wave function for the gravitational field hints at an effective dimensional reduction of spacetime. At very small scales, its behavior becomes similar to a two-dimensional theory in certain diagnostics, which helps blunt the ultraviolet surge that causes trouble in naive quantization and offers an intuitive reason the fixed point can exist. What would it mean for you, observationally, if the world's deep ultraviolet is governed by such a fixed point? Start with cosmology, where the early universe probes extreme energies. In an asymptotically safe scenario, the strengths of gravity and vacuum energy become scale-dependent, so the equations that guide expansion pick up controlled corrections at high curvature. Some versions naturally generate a phase of near-exponential growth without introducing a separate inflaton field. Others modify the initial conditions of fluctuations so that the statistics of the earliest ripples differ slightly from the textbook patterns. None of this is free magic. The predicted shifts are small and model-dependent, but they translate into concrete targets in the cosmic microwave background and large-scale structure surveys, subtle scale dependencies, tiny deviations from perfect Gaussianity, and perhaps a built-in mechanism that avoids a singular beginning by smoothing the approach to extreme densities. On the astrophysical side, a scale-running Newton coupling could tweak how very compact objects form and radiate, with effects that would hide in the noise for ordinary stars but might change the late time damping of gravitational waves from the most violent mergers or shave a sliver off the shadows of the most massive black holes. Again, not as spectacle, but as a bias detectable with patient statistics. In particle physics, asymptotic safety plays nicely with the idea that the strong and electroweak sectors already work as quantum field theories. You can couple matter to gravity and watch the joint flow. For specific matter contents, the gravity fixed point can even shepherd otherwise problematic matter couplings into safe trajectories, suggesting a path to a unified high-energy completion without adding whole new towers of particles. The most practical payoff is conceptual discipline. Instead of declaring that quantum gravity must be something entirely different from quantum field theory, asymptotic safety proposes that gravity is a quantum field theory, but of a particularly subtle kind whose well-posedness relies on a non-perturbative fixed point you can hunt with calculational tools you already trust in other contexts. It's healthy to carry the caveats with the same care as the promise. Fixed points are found in truncated spaces, and while steadily enlarging those spaces keeps returning the same qualitative story, a theorem is still missing. Gauge choices and regulator details can nudge intermediate numbers, and though universal quantities stabilize as you improve the analysis, they demand vigilance. Coupling realistic, chiral matter and matching the full precision of collider and astrophysical data is work in progress, and there is no single smoking gun signature. Just a family of small, correlated consequences spread across cosmology, gravitational waves, and high-energy scattering that, together, would make the case. Even so, the approach is testable in the only honest way frontier ideas are: by consistency across scales and by predictions that get sharper as computations mature. And the deeper philosophical lesson is gently liberating. You don't need to choose between wild new principles and resignation in the face of infinities. You can ask whether the map of theories has a self-organizing structure that saves you from the cliffs. And you can check the answer by calculation rather than charm. In that light, the ultraviolet stops being a place where reason ends and becomes a regime where the same renormalization logic that rescued the strong and electro-weak forces might rescue gravity too, not by shrinking it to nothing but by letting it stand at full height, balanced by a fixed point that continues to guide it even as you turn the resolution knob through decades of scale. If you carry one operational image with you, let it be this: zooming into nature is like changing the aperture on a camera. The colors of your theory shift as some features saturate and others emerge. But if asymptotic safety holds, there is a setting at the smallest scales where the picture stops bleaching out and settles. The shapes remain crisp and only a few parameters, focus, exposure, white balance, need your hand. Everything else composes itself. And as you set the camera down, the mood can be quiet rather than triumphant. The hope is not for fireworks at the Planck frontier, but for coherence, a world where the same language that explains nuclei and semiconductors also explains spacetime, disciplined by a fixed point that keeps curiosity from sliding into paradox, and inviting you to keep asking sharper questions because the theory, at last, can afford honest answers all the way up. Doubly special relativity intuitions. You've grown comfortable with the idea that special relativity protects one universal speed. But a quiet question waits at the edge of quantum gravity. What if nature also protects a second universal scale, the tiny length associated with the Planck realm, or, equivalently, a huge energy? And what would it mean to honor both without picking a preferred frame? Doubly special relativity is the name for that intuition, and its guiding promise is modest yet bold. Keep the spirit of Einstein's postulates. No special observers, the law's the same for everyone moving at constant velocity, while reshaping the transformations between observers so that not only the speed of light but also a Planckian yardstick refuses to change when you boost. You can feel why this is attractive without symbols. Ordinary special relativity tells you that rulers and clocks squish and stretch depending on motion, so a fixed microscopic ruler sounds impossible. But DSR proposes that the squishing acts differently once energies approach the Planck scale, in a way that leaves low-energy physics untouched and only gently deforms the rules where quantum gravity is expected to matter. The trick is to move the action from space-time to momentum space. Instead of asking positions and times to carry the new invariant directly, you let the geometry of energy and momentum carry a subtle curvature, so that when you boost to a fast-moving frame, you travel along gentle arcs in this curved momentum space, rather than straight lines. And those arcs are chosen so the Planck energy remains the same for all inertial observers. The payoffs and pitfalls come into view once you ask operational questions like, does light still move at one speed? And do high-energy particles obey the same thresholds for reactions? Because DSR allows, in some versions, tiny energy-dependent shifts in how waves propagate. So tiny that they vanish for everyday photons but could, in principle, show up for the most energetic flashes the universe throws at us. That possibility makes gamma-ray bursts and blazer flares natural arenas. By timing the arrival of photons across a huge energy range, from explosions billions of light-years away, astronomers can look for a consistent dispersion, high-energy photons slightly earlier or later than their softer siblings. And so far, careful analyses find that if such a drift exists, it must be smaller than 1 part in many quadrillions. A stern reminder that any DSR effect must be extremely suppressed or crafted to avoid linear in-energy delays. Here DSR differs crucially from naive Lorentz violation. The point is not to pick an ether-like rest frame and break symmetry, but to deform the symmetry so all observers agree on the same Planckian guardrail while still agreeing there is no preferred frame. like changing the rules of perspective so distant objects never shrink below a minimal apparent size without changing who is really head-on. That deformation has consequences beyond speeds, particle reactions that depend sensitively on kinematic thresholds, such as whether ultra-high energy cosmic rays should be stopped by the microwave background, become probes, because DSR can tweak the bookkeeping in ways that either raise or lower those thresholds a hair. The observed spectrum of cosmic rays, with its hallmark suppression at the extreme end, already leans hard on theories that would have predicted big departures. But deformed symmetry models can thread the needle by adjusting how energy and momentum add when you compose many quanta, which leads directly to a notorious practical challenge dubbed the soccer ball problem. If microscopic momenta add nonlinearly, why doesn't a literal soccer ball, composed of many particles, immediately reveal new physics when you kick it? Sensible DSR constructions answer by ensuring that the non-linear addition fades for aggregates, or by building a composition law that respects low-energy linearity while encoding only Planck-suppressed corrections for genuinely Planckian constituents, keeping macroscopic bodies safe. Push a little further and a deeper idea emerges. If momentum space carries curvature, then the notion of meeting at the same place at the same time can become energy dependent, a concept called relative locality, so that different observers, comparing events involving ultra-energetic quanta, may need to insert tiny, frame-independent corrections to decide whether world lines intersect. This sounds exotic, but it's a controlled form of bookkeeping that preserves causality in the domain where it has been tested, while warning you that at stupendous energies, the operational meaning of coincidence needs care. Mathematically, people encode these deformations in algebras whose commutators no longer match the textbook Poincaré ones, or in non-commutative spacetimes where coordinates resist being simultaneously sharp. But the physical message you can carry without formalism is simple. DSR keeps the symmetry ethos, shifts the geometry to places we rarely look, momentum space, composition laws, and asks for effects that are faint, observer-agnostic, and Planck-scaled rather than loud violations that a single clever lab could have found a century ago. The observational ledger remains largely quiet. Instruments on satellites and ground-based telescopes have slashed the parameter space for any energy-dependent light speed, and collider kinematics still looks stubbornly ordinary. But that silence is not the same as a verdict, because many consistent DSR models predict no leading-order time of flight delays and push their novelty into regimes we cannot yet reach. Meanwhile, the conceptual dividends accumulate. By insisting on a second invariant scale without sacrificing inertial democracy, DSR teaches you how symmetry itself might be resilient under deformation, a lesson that dovetails with broader hints from quantum gravity that measure the shape of theory space rather than any one equation. If you want a concrete way to talk about tests without drowning in detail, focus on three families: timing tests with astrophysical photons and neutrinos that hunt for minute, distance-amplified dispersions, so far null within impressive bounds; threshold tests in cosmic rays and very high-energy gamma rays that look for shifted cutoffs. Present data prefer either no shift or one buried beneath astrophysical uncertainties; and coherence tests that track wave packet distortion across astronomical baselines. No smoking gun yet, again pushing viable DSR models toward ultra-subtle predictions. The healthy skepticism you should keep is that deforming symmetry is not a license to fit any curve. A serious model must present a consistent calculus of boosts, composition, and conservation, reduced to exact special relativity at accessible scales, and avoid hidden preferred frames that reappear under stress. The reward for that discipline is not spectacle, but coherence. A framework where the Planck scale is as kinematically sacred as the speed of light, where spacetime's granular whispers can be acknowledged without tearing down the global stage that has served us so well, and where any departure from textbook behavior is locked behind conditions so extreme that the cosmos itself becomes the only laboratory big enough to try. Let that land gently as a closing thought. DSR is less a claim that everything changes, and more a lesson in how principles bend before they break, a quiet architecture that prepares you for the day When a burst of light or a rain of cosmic particles nudges our clocks out of perfect agreement by an amount too disciplined to be noise, and just enough to reveal that the universe keeps two promises at once: no preferred clocks, and a smallest meaningful tick that all clocks respect: generalized uncertainty in gravity regimes. You were told that uncertainty is a quiet trade. Squeeze position and momentum gets noisy. But gravity adds a new clause to the bargain, and it changes the tone from a classroom exercise to a rule of survival. If you try to pinpoint where something is with too much energy, the energy you use weighs on spacetime itself, warping the very region you're trying to resolve. And if you push hard enough, that warp can hide the target behind a tiny horizon. That observation, which you can reach with thought experiments rather than equations, sits behind the idea of generalized uncertainty in gravity regimes. A family of proposals that say the familiar quantum blur tightens at first as you increase probe energy, then fights back because gravity refuses to be a passive stage, and the net effect is a minimal measurable length that no clever tactic can beat. Here is a way to feel it without symbols. Imagine a microscope that uses photons to locate a particle. To see finer detail, you raise the photon energy, and quantum mechanics agrees. Shorter wavelength, sharper position. But gravity points out that high-energy photons gravitate, pack enough energy into the focal region and space-time buckles, first adding noise, then, in the extreme, forming a micro-black hole that swallows what you hope to see. So there is a sweet spot you cannot surpass, not because your optics are bad, but because the world prohibits better. And the scale of that impasse is set by the same combination of constants that measures when quantum and gravity should both matter. Other thought experiments echo the same verdict from different angles. Build a perfect clock and you'll find that making it light to reduce its gravitational field makes it jitter more by quantum recoil, while making it heavy to stabilize its ticks curves spacetime around it and spoils simultaneity. So timekeeping, too, has a best possible precision once gravity is admitted. Try to send information through a tiny channel at blistering bandwidth, and you face limits that mix computation with mass energy, because the energy stored in the device to hold and process bits eventually threatens to collapse the channel. All of these stories point to a shared intuition. There is a Planck-flavored barrier to arbitrarily fine localization that does not come from engineering weakness, but from the joint demands of quantum and geometry. Turning that intuition into a usable rule, people write generalized uncertainty relations that add a gravity-aware correction to the ordinary product bound, typically introducing an extra term that grows with the probe energy. You don't need to memorize forms to grasp the message. The curve of achievable position resolution versus probe energy bends down and then up, hitting a lowest point at a tiny but non-zero length. Proposed forms differ. Some grow with the square of energy, some add a linear piece, and those differences matter because they encode distinct assumptions about how quantum measurements back-react on spacetime. But they all agree on the qualitative shape of the trade-off and on the existence of an operational flaw. That flaw is crucially observer-agnostic. In credible constructions, you don't sneak in a preferred frame to get it because the modification lives in commutation rules or in the geometry of momentum space rather than in a rigid grain nailed to a specific rest system. As soon as you accept even the possibility of such a flaw, consequences ripple outward in ways you can check. Wave packets cannot be shrunk indefinitely, so there's a lower bound on the spread of any particle's position. Bound states acquire tiny shifts in their energy levels compared with textbook values. Oscillator ground states, atomic spectra, and solid-state vibrations pick up corrections that are suppressed at everyday energies by enormous ratios, but in principle, measurable if your apparatus is designed to amplify them. Cavity optomechanics and cold atom interferometry exploit exactly that strategy. Use macroscopic coherence and long interrogation times to turn microscopic deviations into phase shifts you can catch, and the null results so far translate into sharp bounds that push any generalized uncertainty effects deeper into the ultraviolet, disciplining the theory by experiment rather than by taste. Gravity-side implications are just as rich. If there is a minimal length, then the cascade of modes that feed Hawking radiation near a horizon cannot extend to arbitrarily high energies in the way naive calculations pretend. Consistent GUP-inspired analyses suggest small, model-dependent tweaks to black hole evaporation curves, sometimes predicting long-lived remnants or modified late-time temperatures, all of which sharpen the old information puzzle into operational questions about how precisely the spectrum deviates and whether those deviations are strong enough to matter before astrophysical clutter buries them. In the early universe, a generalized uncertainty bound reshapes the initial spectrum of quantum fluctuations that later grow into galaxies, slightly altering the balance between very long and very short wavelengths, or imprinting faint non-Gaussian fingerprints, effects that precision cosmology can hunt, but that must be subtle to survive the already tight data. Even the humble process of scattering at extreme energy feels the constraint. If positions cannot be idealized as points below the minimal length, then cross-sections and form factors must be reinterpreted with effective smearing, a built-in regulator that tames ultraviolet pathologies without guesswork. Philosophically, the upgrade from Heisenberg's product to a gravity-aware trade-off changes what you think a measurement is in a gravitational world. Not a passive readout of pre-existing values, but a two-way interaction in which the apparatus's own field becomes part of the story, so that asking too hard a question about where modifies the landscape on which where is defined. That is why the cleanest derivations anchor themselves in operational setups, clocks and rods with mass, beams with finite energy, detectors with finite size, rather than in abstract algebra alone. It's healthy to carry skepticism alongside the excitement. There is no unique, universally accepted form of the generalized relation, and different communities prefer different packages, depending on whether they start from thought experiments, modified commutators, discrete geometry, or deformed symmetries. Some versions flirt with conflicts with cherished principles unless they are built carefully. Energy dependence of measured speeds, composition laws for many particle systems, or apparent violations of equivalence when you push too hard. And consistent models work to keep those issues at bay by ensuring low-energy physics is exactly standard, by making corrections observer invariant, and by hiding non-linearities in ways that wash out for macroscopic aggregates. On the data side, the scoreboard is honest. High-energy astrophysical timing, watching gamma-ray bursts for energy-dependent arrival delays, has not demanded any correction of the simplest, naive kind. Laboratory interferometers have found no smoking gun in the phase noise of ultra-sensitive mirrors. Atomic clocks comparing isotopes at absurd precision have not revealed the telltale shifts a large universal minimal length would force in transition frequencies. Far from being discouraging, these nulls are a success. They carve away sloppy versions of the idea and leave only those consistent, deeply suppressed deformations that fit both the spirit of quantum gravity and the letters of experiment. The payoff for keeping the refined versions is twofold. Conceptually, you gain a clear story about why the continuum is a good approximation, because attempts to outrun it trigger gravitational backreaction that restores humility. And practically, you gain a disciplined set of targets for the next generation of tests. From quantum sensors that push mass and coherence into new regimes, to tabletop analogs of horizons that can check whether mode cutoffs leave their imprint on thermal spectra, to cosmological surveys that tighten the error bars on primordial statistics, where Planckian corrections might survive the eons. Let the lesson end softly. Generalized uncertainty in gravity regimes is not a claim that nature becomes unintelligible at small scales. It is a promise that intelligibility is preserved by a new kind of kindness. The world refuses to let you isolate a region so tightly that your question would destroy the context needed for an answer. In that light, the minimal length is not a brick in the wall, but a guardrail along a mountain road, invisible when you drive well but decisive when you stray, ensuring that precision deepens understanding without letting curiosity push the fabric of space and time past the point where its own meaning frays. Black hole mining and quantum limits. You picture a dark engine in the sky and wonder not just what it hides, but what you could harvest from it. The audacity is ancient, the physics modern. A rotating black hole stores real, usable energy in its spin, and gravity stores free energy in the way light and matter fall. So the question becomes how much you can extract without breaking the rules that make the universe honest. And the answers trace a precise boundary between cleverness and impossibility. You start gently by imagining a patient miner with a strong winch and an indestructible cable lowering a small device toward the horizon, because near that edge the redshift turns even modest fuel into a jackpot for faraway observers. The energy you haul out can exceed what you fed in if you choreograph the drop and lift correctly, yet immediately the laws of black hole thermodynamics intervene. The horizon has a temperature set by its mass and a surface gravity that plays the role of acceleration. So anything you try to hold close feels a bath of particles that press upward like radiation in a furnace. A buoyant push that keeps your device from getting arbitrarily near. Proceed anyway, and you learn the first hard limit, a version of the second law updated for horizons. Any scheme that reduces the black hole's area must pay entropy elsewhere, and the minimum payment is not optional. If you lower a box of hot gas to just above the horizon and open it to dump the gas in, the floating effect and quantum noise conspire to ensure that the lost area is balanced by the entropy you carried. And if you try to cheat by making the gas colder or the box tighter, the very act of localizing energy adds uncertainty and recoil that ruins the bargain, as if the whole insisted on a fair price for every reduction in its size. Shift gears to the spin itself and a cleaner engine appears. A rotating black hole drags space around with it, and if you send in a carefully aimed package, an object or even just a wave, so that it splits, with one piece falling in against the spin and the other escaping, the escapee can carry away more energy than you sent, fed by the hole's rotation. A thought experiment that becomes practical in waves through a process where certain tones bounce off the hole and return louder, extracting rotational energy. Now replace your package with a magnetic field and plasma, the stuff galaxies provide naturally, and the same geometry drives electric currents that launch spectacular jets, which is why real black holes power beacons we can see across the universe. But even here you cannot run the meter to infinity. As you spin a hole down, it cools, its temperature and radiation change, and at every step, the generalized second law, bookkeeping that counts both ordinary entropy and the horizon's share, keeps score so that no sequence of maneuvers can reduce the total ledger. Return to your winch and think more carefully about the throat you are working near. The closer you hover, the hotter the bath feels because acceleration itself makes the vacuum look thermal, and your cable and motor must survive that heat and tidal stress. Real materials have limits. So even before you hit deep quantum constraints, engineering caps the depth of the well you can reach. Theorists then push past engineering with honest quantum limits. Negative energy, needed for certain exotic tricks, is allowed only in tiny, fleeting doses, bounded by inequalities that prevent you from piling up enough to cancel the thermal pressure or to pry open sustainable shortcuts. You discover that any plan to refine the mining, cycle after cycle, lower and lift, or a carousel of mirrors to boost favored wave, tones, runs into speed limits set by how fast information and energy can be processed without melting your apparatus or collapsing your tether under its own stored energy. Even the dream of perfect timing meets a wall. The more precisely you try to synchronize to the horizon's dragging, the more your clock must weigh to resist jitter, and the more it weighs, the more it distorts the very spacetime you're timing. A quiet self-consistency check that pushes you back from fantasy toward feasible margins. The sharpest insights arrive when you book everything as a thermodynamic business. The horizon's temperature sets a floor on waste heat. The physics of computation sets a cost for the control you need to steer wave packets and tethers, and the limited rate at which you can extract free energy from the spin without choking the engine. Too much back reaction, and you spoil the geometry that made extraction possible. Fixes a maximum power in clean models. If you try to speed run the process, turbulence in the plasma, noise in your control loops, and the finite time needed for waves to circle and amplify together shave your gains. If you try to get cute by lowering perfectly reflective mirrors or ultra-thin strings right to the edge, quantum fluctuations of the radiation pressure rattle them, and the string's own mass and tension reappear in the accounting, so that infinitely light tools are replaced by tools that heat, stretch, and sometimes snap. Even philosophy must sit a step back. Mining does not give you a backdoor into forbidden causality or a loophole around information bookkeeping. The radiation you harvest carries what the state allows it to carry, and any dream of sucking out secrets faster than the laws permit runs into the same wall that keeps paradoxes at bay elsewhere. Recovering fine detail out of a scrambled system is not forbidden, just punishingly slow and resource-hungry. So the practical image you carry away is less a fantasy of cosmic strip mines and more a disciplined set of levers that nature recognizes and pays out on. Rotational energy in a spinning hole can be drained by waves and fields under conditions we understand and even witness on galactic scales. Near-horizon gradients can be harnessed to an extent, but they come bundled with radiation pressure and noise that rising technology can never quite outrun. And quantum limits, the gentle but firm restrictions on negative energy, on localization at fixed power, on timing without back reaction, close the door on the most extravagant loopholes. And yet the story remains marvelously generous, because even with all those limits, the world leaves room for strategy. If you want power, build a magnetic dynamo across a rotating hole and let the dragging of space do the heavy lifting. If you want purity, shape waves to ride the amplification bands and accept moderate gains spread over many cycles. If you are a thought experimentalist, lower small systems slowly enough to surf the redshift and return with more work than you spent, while respecting the buoyant pressure that tells you where the horizon's thermal influence begins to bite. And if you are a philosopher at heart, let the closing mood be patient rather than deflated. Black hole mining does not promise miracles. It offers a curriculum, how to think about energy, entropy, and control in the most extreme laboratory the universe gives you, with every limit an invitation to refine the question. In that curriculum, the headline is simple. You can take from a black hole without lying to physics, but you cannot take more than the ledger allows, and the ledger is kept not just by gravity's pull, but by the quiet quantum costs of precision, timing, and heat. Accept that balance, and the dark engine stops being a myth or a trap and becomes what it has always been for the cosmos. An honest machine, efficient but fair, whose power you may tap only to the extent that you honor the rules that make power meaningful at all. Soft hair, conserve charges at infinity. You expect nothingness at infinity to be a quiet backdrop that forgets details, but gravity and gauge theory insist on a subtler ending to every story. The faraway edge of spacetime keeps books, and the entries it records, soft, zero-energy-like imprints carried by long wavelength quanta, are what physicists call soft hair, an infinite family of conserved charges that live not on a surface you can touch, but out at null infinity, where light rays finally come to rest. The idea is easiest to feel if you start from a collision and ask what remains after the fireworks fade. 2 stars scatter, or a black hole absorbs and later emits. And although the fast waves pass, detectors at great distance are left with a tiny, permanent change. Free-falling mirrors drift apart by a fixed extra amount. Test gyroscopes pick up a minute twist, and radio arrays notice a step-like shift in phase. Signatures of the memory effect telling you that long, soft gravitational waves have carried a bookkeeping message outward. This is not a quirk, but a consequence of symmetry. At infinity, the Einstein equations allow not just the familiar translations and rotations, but a vast enlargement, super translations and, in refined treatments, super rotations, angle-dependent nudges that map physically distinct vacua into one another. So there isn't a single empty state, but a whole landscape of them, and which one you end in after an event is dictated by conserved charges that balance incoming and outgoing radiation. The beauty is that 3 seemingly different statements, universal soft theorems saying that the probability for emitting a very low-energy graviton or photon is fixed by the hard event, the memory left in detectors, and these asymptotic symmetries are actually the same triangle told in 3 languages. So when something dramatic happens in the middle of the universe, infinity is not indifferent. It adjusts its charges in a way you can, in principle, read. Black holes join the story with a twist. Classical no-hair theorems said a settled hole keeps only mass, spin, and charge. But when you include the soft sector, the horizon and the sky at infinity support additional, delicate, labels, configurations of low-frequency fields that cost essentially no energy, yet still carry which-way information about what passed, hence soft hair. It's tempting to leap and say this is the whole answer to black hole information. Puzzles. But honesty helps. Soft hair is a necessary part of the ledger. Ignoring it makes even scattering among ordinary charges inconsistent. But whether it is sufficient to encode all the microscopic detail of everything that fell in remains an open question. Still, working out the consequences already teaches you to pose better testable questions. If a black hole absorbs matter with a particular angular pattern of radiation and later evaporates, the net soft charges at infinity must reflect that pattern. If two otherwise identical mergers differ in how they radiate at the end, because of kick directions or asymmetries, then their final soft charges differ, and the permanent displacements and velocity memory in gravitational wave detectors will, with enough sensitivity and statistics, sort histories into families. Experiments are edging into this regime. LIGO Virgo Kagra can, in principle, see the gravitational memory as a slow step-like rise at the tail of a waveform. Pulsar timing arrays look for correlated timing drifts across the sky that include a memory component. Radio teams chase the electromagnetic cousin, EM memory, as a lasting offset in field integrals after bright flares. None of these is a stunt, because the same soft sector that puts memory in your data is also what cures infrared divergences in theoretical calculations. If you pretend the vacuum is unique and forget about soft quanta, multiphoton, and multigraviton emission probabilities, blow up, dress hard particles with coherent soft clouds, or work with S-matrix elements between appropriate vacua at different supertranslation angles, and the infinities cancel. A consistency check that soft hair is not decoration, but infrastructure. Operationally, you can think of infinity as a diffuse detector with infinitely many pixels labeled by angle, each pixel enforcing a conservation law that balances changes in the hard momentum flowing through it with the flux of soft quanta that end in that direction, and the sum over all pixels encodes the total shift of the vacuum. Even horizons get a version of this bookkeeping. You can define charges on cuts of a black hole horizon that respond to soft radiation threading the edge, and though those horizon charges can be re-expressed at infinity by following null rays outward, picturing them on the horizon helps you see why the no hair slogan was too strict. There is structure there, albeit delicate and easily scrambled by subsequent info. The constraints are not merely philosophical. Soft theorems fix the leading low-frequency tail of any waveform, which bounds how much memory a source of given energy can produce. And asymptotic symmetry arguments show that certain patterns of late-time radiation are forbidden unless accompanied by compensating soft flux, offering a way to cross-check numerical simulations of mergers against deep conservation laws. On the quantum side, the charges act like custodians of which vacuum you occupy, and transitions among vacua are inevitable whenever you accelerate charges or shake mass distributions. So the universe is constantly writing to the soft ledger even in mundane processes, a slow drift that, integrated over cosmic history, could in principle carry a fossil record of many small acts. Practical limits keep the romance grounded. Soft hair is subtle. It doesn't let you decode diaries wholesale from hawking quanta. It doesn't open wormholes, and it doesn't license violations of causality. And real detectors suffer from seismic noise, thermal drift, and calibration headaches that make the clean, step-like memory hard to isolate. Even conceptually, some of the extended symmetry is still under active debate. Superrotations invite careful definitions to avoid pathologies, and matching the full quantum notion of hair to specific countable microstates of a whole requires stitching to a microscopic theory of gravity that we don't yet own. Yet the trend line is steady. Where once infinity was a boundary condition, now it is a dynamic participant. Where once vacuum meant unique nothing, now it means a family of nearly nothings distinguished by soft labels. And where once no hair was a mantra, now soft hair is a reminder to include the quiet, long wavelength end of the spectrum in every conservation law. If you want a concrete picture to carry home, imagine every violent astrophysical event as a concert that ends with a final chord held so gently you barely notice it, a persistent offset in the air pressure that never quite settles back to zero. And imagine the sky at infinity as the room itself, keeping that offset as a record that the song was played. We are learning slowly to hear those held notes in waveforms tales, in angle-dependent conservation laws, in the infrared structure of quantum amplitudes, and, one hopes, in direct detections of memory that turn the abstract charges of asymptotic symmetry into entries in an experimental logbook. And when you let the thought quiet, the moral is soft but clear. The universe does not bury everything it has done. It leaves the faintest fingerprints at its edges, conserved not by decree but by the gentle accounting of fields that never quite go to zero. Hair so soft you'd miss it if you didn't know where to look, yet strong enough to keep truth from being shaved clean away. Gravity as entropic or emergent force. You've always met gravity as a promise about curves and falling, a clean geometric rule that tells apples and planets how to move. But there's a different, unsettling invitation you can test with your own intuition. What if gravity is not a fundamental push or the curvature written in stone, but the large-scale pressure of information itself, an entropic or emergent tendency for systems to drift toward arrangements with more invisible microstates, the way perfume diffuses, or a stretched rubber band pulls back, because there are simply more ways for its molecules to be slack than taut. Begin gently with a walk you can picture. Hold a small object just outside a notional screen, a surface that stores bits about what's inside, and imagine that as you move the object, the number of microscopic arrangements compatible with your coarse view changes. So the system does what all systems do. It leans toward the side with more ways to be, and that lean looks like a force. The underlying idea is mundane and powerful. Entropy gradients create effective pushes, from osmosis to polymer elasticity, and if spacetime has information-bearing degrees of freedom woven into its fabric, then motion toward more configurations can masquerade as gravity. This isn't a handwave born yesterday, long before bold proposals. A quiet landmark showed that Einstein's field equations themselves can be read as a thermodynamic balance. When you slice spacetime locally by a tiny, light-like patch and ask for the Clausius statement of heat flow to hold for every such patch, energy flux across the slice must equal temperature times change in entropy. You recover the geometric equations that normally take center stage. That result doesn't say atoms of spacetime are known. It says, treat these equations like equations of state, the way pressure and temperature emerge from molecules you don't see. Later, others asked whether the familiar inverse square tug might be rephrased as a response to how information is stored on coarse-graining surfaces, weaving in the observation that horizons, from black holes to accelerating observers, come with temperatures and entropies, and that small displacements relative to a horizon change that entropy by a definite amount. In this picture, the attraction you feel is not a mystical pull, but the statistical urge of a system to increase a count of unseen configurations. With your trajectory, the visible compromise between energy you carry and information the world prefers to spread. Beyond philosophy, the entropic route earns its keep by reproducing staple results in simple settings. Treat a notional screen as carrying a specific information density. Let energy inside obey ordinary equipartition. relate temperature near the screen to acceleration, the way accelerated observers inherit a bath of radiation, and Newton's law falls out as the gentle limit of a broader information bookkeeping. Yet the real reason to care is methodological rather than algebraic. Thinking in terms of entropy and information reveals why so many gravitational phenomena speak an area language, why horizons measure their disorder on surfaces rather than volumes, why coarse-grained counts keep time with geometry, and it ties gravity to the same thermodynamic logic that powers engines and explains why stretched polymers pull back. This frame also invites you to look for emergent gravity in laboratory cousins. In certain fluids, collective excitations propagate as if they lived in a curved background, and horizons and thermal spectra appear for effective waves, even though no one curved the water. A small lesson in how geometry-like behavior can blossom from microdynamics that never mention geometry at all. Carrying that lesson back, some versions of emergent gravity go further and ask whether departures from the simplest entropic bookkeeping could mimic the astronomical oddities you usually attribute to dark matter. The extra rotational support in galaxies, the tight relations between visible mass and orbital speeds, by adding a new, state-dependent elastic response of the information storage medium we call spacetime. Preliminary fits to some galactic data can be encouraging, and the approach predicts subtle deviations in lensing and dynamics that observers can check. But this is where sobriety is essential. The universe is a stern examiner, and large-scale structure, precise cosmic background maps, and collisions of galaxy clusters set exacting constraints that any emergent alternative must face without special pleading. In parallel, the entropic lens shines a kinder light on otherwise puzzling facts. Time-dependent horizons carry a notion of heat and entropy flux that aligns with energy conditions. Gravitational waves carry information whose flux at infinity ties to gentle conservation laws. And the fidelity between different coarse grainings of a region, how much two descriptions can agree, tracks how stiff or supple the emergent geometry should be, suggesting that curvature might be the macroscopic elasticity of information flow. Still, you should keep two guardrails. First, calling gravity entropic does not license sloppiness. Every successful prediction of general relativity must be recovered in the appropriate limit, from light bending to the precession of Mercury to the recent catalogue of gravitational wave events, and any new terms must arrive in regimes where data still leave room. Second, emergence is not an excuse to ignore microphysics. If spacetime has information-bearing constituents, we should sharpen what they are, how they interact, and why their collective behavior trims neatly to known equations over an astonishing range. The good news is that you have concrete questions to press. Do entropic derivations hold beyond static, spherically symmetric cases in fully dynamical, strong field events? Do the implied information densities and temperatures remain consistent with the absence of observable noise in precision experiments near Earth? Do proposals that attribute galaxy phenomenology to an emergent elasticity survive gravitational lensing maps that probe mass in entirely different ways? And can an entropic approach naturally accommodate the success of dark matter in matching the cosmic web, while still explaining galactic regularities without fine-tuning? None of these are rhetorical. They are being asked with growing care as data improve. The quiet payoff, even if you eventually decide that dark matter remains the best account, and that gravity's standard geometric form is fundamental, is that the entropic frame changes how you learn. It teaches you to read gravitational laws as the thermodynamics of ignorance, relations among quantities that summarize vast micro-detail, and it suggests new experimental targets, tiny, state-dependent corrections near horizons, constraints from the noise budget of accelerated observers, statistical tie-ins between matter distributions and effective elastic responses that don't appear as clearly in the purely geometric story. Let the thought land softly. You need not choose a camp to benefit. Geometry remains a brilliant language for prediction, but it may be the large print version of a story whose fine print is thermodynamic. In that story, gravity is less a command than a consensus, the way a crowd flows toward open space not because anyone issued an order, but because there are more ways to move freely in that direction. And when you step away from the page, the world doesn't feel thinner, it feels sturdier, because even if the stage of spacetime is ultimately fundamental, you now understand why so many of its rules rhyme with the logic of heat and information. And if the stage is emergent, you've begun to see how warmth, chance, and counting could have written the law that makes apples fall and galaxies hold. Gravitational decoherence proposals. You've seen how ordinary noise makes quantum delicacy fade, warm air jostles, photons scatter, surfaces vibrate. But there's a more austere suspicion you're invited to consider. Even if you silenced every stray molecule and turned out every light, might gravity itself be enough to wash quantum superpositions into classical facts? Not by magic, but by the way mass and spacetime refuse to share two incompatible stories at once. That is the heart of gravitational decoherence proposals, and to hold them cleanly, you should separate three tones that sometimes blur together. One says, gravity behaves like any other environment and adds a subtle, unavoidable dephasing to quantum states. Another says gravity is not merely a bath, but the judge that collapses superpositions objectively when the two branches curve spacetime too differently to coexist. A third says gravity can remain fully quantum, and the real test is whether it ever helps create entanglement. If it can, then it isn't just a classical noise source. Begin with the gentlest version, the environmental one you can picture without equations. A composite object in a superposition of two heights does not just hang there. Each branch ticks time at a slightly different rate because clocks run differently in slightly different gravitational potentials. So all the little internal oscillators inside the object, vibrations, spins, electronic levels, slowly slip out of step between the two branches. Viewed from outside, those internal clocks are hidden, but their phase mismatch leaks witch path information, and the interference fringe fades even though you never touch the object. The strength of this effect grows with time, with how high you split the paths, and with how warm and clock-filled the object is, so ultra-cold atoms suffer it barely at all while messy. Room temperature objects would see it much more if you could maintain a coherent superposition long enough. The idea is operational and conservative. It doesn't modify quantum theory. It simply admits that gravity changes proper time, and therefore the internal phases that any composite carries, turning spacetime's gentle time dilation into a quiet source of dephasing. A second, bolder family of proposals goes beyond dephasing and flirts with objective collapse, and you can feel its logic by imagining a tiny bead held in a superposition of two places. Each branch demands its own mass distribution and thus its own gravitational field, and the difference between those fields stores a kind of gravitational self-energy of the superposition. The claim is that nature refuses to let that energy remain unpaid indefinitely, and after a characteristic time set by how much the two mass distributions disagree, the state picks a side, no detector required. In this picture, the larger and more separated the branches, the faster the collapse, which is why microscopic particles behave quantumly for eons, while mesoscopic lumps would, in principle, localize quickly. This is not the same as everyday decoherence by air or light. Even in perfect isolation, the state would choose, because the conflict is intrinsic to the superposition's gravitational footprint. Skeptics ask whether such a law can be written consistently without violating energy conservation or letting you signal faster than light. And careful versions work to avoid those traps by encoding the new ingredient as a stochastic, universal field whose noise has just the right spectrum to drive localization without free energy dividends. Whether the universe actually uses this rule is an experimental question, not a matter of taste. Between these edges lies a practical middle, theories of fluctuating spacetime that treat gravity's low-level jitters like a very cold but non-zero bath. Long wavelength gravitational waves slosh through the lab, distant masses rumble, the ground tides minutely, and all of that shows up as phase noise in exquisitely sensitive interferometers. You can compute the expected dephasing from these known backgrounds and compare it to other mundane culprits: residual gas, blackbody radiation, patch potentials, trap vibrations. And the sober verdict today is that ordinary noise wins by orders of magnitude unless you take heroic steps to suppress it. That sobering point is a gift. Any claim to have seen gravitational decoherence must clear a high bar of environmental accounting, and that requirement has shaped the new generation of experiments. Those experiments sketch a path you can read as a story of increasing mass, increasing space and better cleanliness. Matter wave interferometers push complex molecules and nanoparticles through beam splitters and search for lost fringe contrast that scales with mass and path height the way gravitational time dilation predicts, while keeping temperature stray light and gas pressure so low that no mundane culprit can explain the loss. Levitated optomechanics suspends nanospheres in optical or magnetic traps, cools their motion toward the quantum ground state, then releases and recombines them, aiming to let gravity's own redshift be the dominant dephaser for the first time. Ultra-long baseline atom interferometers stretch freefall times so far that even the tiniest gravitationally induced phase slips can accumulate. And space-based concepts promise microgravity quiet, where seismic and thermal noise no longer drown delicate effects. Across all of these, the signature of the time dilation mechanism is precise. Defacing should depend on the internal energy spread of the object and on the gravitational potential difference, not merely on mass or size. And disentangling that dependence from every other knob is the experimenter's art. If the objective collapse camp is right instead, the signal would look different. A mass and separation-dependent loss of coherence that does not care about internal clocks and refuses to be reversed by clever spin echoes or dynamical decoupling. A clean size law for localization time that scales with how different the two mass layouts are. Tabletop tests are now designed to attack that possibility head-on by engineering large, spatially separated superpositions with minimal heat and light, watching whether visibility falls faster than all known dephasers allow. In parallel, high-Q mechanical resonators are monitored for excess noise that would betray a universal collapse field, gently jiggling everything, and bounds from those hearing tests already carve away sloppy parameter choices that would have made the effect easy to see. There's a third decisive fork you should hold onto because it reframes the whole debate. If gravity is merely a classical channel that adds noise, it can never generate entanglement between two initially unentangled systems, whereas a genuinely quantum mediator can. So proposals have been crafted where two tiny masses are shielded from all known forces and allowed to interact only gravitationally while their spins serve as flags. If, after time, the spins end up entangled, no classical additive noise model of gravity can explain it, and the case for a quantum gravitational field strengthens. If, instead, all you ever see is extra dephasing, the balance tilts the other way. This entanglement or not criterion is crisp, falsifiable, and it forces gravitational decoherence ideas to say exactly what they permit or forbid, turning philosophy into a bench test. Throughout, consistency keeps everyone honest. Any added dephasing must respect relativity's causal structure and avoid letting savvy experimenters harvest work from noise. No perpetual motion loopholes. Any collapse law must be written so that macroscopic objects don't glow from inexorable heating. Any time dilation mechanism must fade to nothing in stationary spacetimes where proper time differences vanish. And every claimed signal must survive changes in geometry, temperature, and interrogation time with the right scalings. It's to the community's credit that most proposals now come packaged with complete noise budgets and concrete, loss-limited numbers rather than hand-waving. What should you expect next, and what would count as real learning? A clean detection of gravitational time dilation, defacing in a regime where all other noise lines sit below the data would confirm that even the quietest spacetime gently blurs composite superpositions. A null result in that same regime would force a rethink of internal clock models, or of how composite structure couples to gravity at low energies. A verified mass and separation law for objective collapse, immune to echo tricks, would rewrite textbooks and demand a new conservation bookkeeping that holds beyond laboratory scales. A demonstration of gravity-mediated entanglement would push the classical noise versions into a corner and make gravitational decoherence a secondary effect rather than the main act. And in every case, The decisive step will be not a single hero experiment, but a weave of cross-checks. Vary mass while keeping geometry fixed. Vary height while keeping mass and internal temperature fixed. Swap platforms to build a picture that points in one direction from many angles. Let the thoughts settle in the tone we've kept. None of these proposals tries to make the world mystical. They try to make it accountable where two honest principles meet: quantum superposition and gravitational back reaction. And they differ only in whether that meeting adds gentle fog, enforces a sharp choice, or, paradoxically, proves gravity belongs in the same quantum club as everything else. As you breathe with that, notice how your sense of fragility changes. Quantum states are not fragile because the world is hostile. They are fragile because the world is interactive. And gravity, being universal, is the one interaction you never get to turn off. The question is not whether it matters, that answer is yes, but how it matters, and whether its touch is merely a soft shiver in the phase, a firm hand on the scale, or the handshake that lets distant masses share a secret. Whichever way the data fall, the lesson will be generous, because a careful measurement that says no is as instructive as one that says yes, and both will refine how you think about time, mass, and the meaning of isolation. And when the lights dim on this topic for tonight, carry a simple image: a tiny sphere held aloft in a silent chamber, exploring two paths at once. Around it, space-time itself is not a blank, it is a participant, faintly tilting the metronomes inside, perhaps insisting on a single path if its patience wears thin, or, if we listen carefully enough, tying the fates of two such spheres together in a whisper only entanglement can decode. Quantum superpositions of space-time. You're used to thinking of space-time as a single, shared stage, one geometry per scene, curves set, clocks agreed upon up to the usual relativistic rules. But the quantum question refuses to stay quiet. If matter can be in superposition and matter shapes geometry, why shouldn't geometry itself be in superposition, with the tick rate, light cones, and even the order of events gently split across alternatives that coexist until a measurement forces a choice? To feel this without symbols, imagine a tiny mass in a carefully prepared here-there state, and place beside each location a good clock. In the here branch, the nearby clock feels a slightly stronger gravitational potential and runs a touch slower. In the there branch, it runs a touch faster. So the joint state of mass and clocks now carries two slightly different stories of time, both valid, both present, and if you recombine the mass paths just right, the phase difference between those stories can reveal that not only the mass but the metric it sources was in limbo. That is what people mean by quantum superpositions of space-time. Not a fantasy of two universes colliding, but the operational statement that all the relational quantities we use to define geometry, tick rates, light travel times, causal order, can be placed in a coherent split and later made to interfere. Carrying that intuition further reshapes familiar questions. In a world with a single background, you can ask where and when things happen absolutely. In a world where geometry is relational and sometimes indefinite, you must phrase questions in terms of what one physical system can say about another. What is the time shown by clock A when light from lamp B reaches mirror C? And those answers can themselves sit in superposition until interactions allow you to compare notes. This is not a license for paradox. It is a demand for relational bookkeeping. Different quantum reference frames can describe the same global state with geometry definite in one description and indefinite in another. The way a particle's momentum looks sharp if you ride with it and blurry if you don't. From that vantage point, several threads tie into a single fabric. One thread is in definite causal order. Ordinarily, you say A influences B, or B influences A, or neither. But quantum mechanics lets you build processes where the order of operations becomes a resource. A before B and B before A in a controllable superposition, already realized with light and matter in non-gravitational devices called quantum switches. Gravity enters when you see that changing who is higher or lower in a gravitational field changes proper time, and thus the effective order in which gates act. So a small mass in a spatial superposition could, in principle, Place the ordering of two operations in a soft superposition via its two metrics, turning causal order into something you can interfere. A second thread is the quantum clock. In the Page-Wooter's viewpoint, time is read off a physical subsystem rather than assumed, and a superposition of gravitational potentials makes the clock subsystem disagree with itself in a measurable way. In tabletop terms, that says if you split an atom's path vertically, let its internal transition play the role of a clock and recombine after long free fall. You're not just measuring a gravitational phase. You're letting two slightly different spacetimes for that atom interfere. A third thread is entanglement as witness. If geometry were only a classical field with noise, it could disturb phases but could never entangle two systems that only talk through it. If it is quantum, it can. So proposals place two tiny masses in superpositions and check for later entanglement in auxiliary spins that start uncorrelated. Success would not only shout, "Gravity can make entanglement." It would quietly say, the metric fluctuations that carried that influence were themselves quantum and coherently shared. These crisp ideas meet. Crisp constraints the moment you reach for them in the lab. Macroscopic superpositions are fragile. Ordinary decoherence is relentless, and gravity's own influence at accessible masses is minuscule. That is why the most credible roadmaps go after signatures with unique scalings. Defacing that grows with gravitational potential differences and internal energy spread, not just size. Entanglement that appears only when electromagnetic and acoustic channels are sealed off. Or interference patterns that shift exactly as the redshift between branches demands. Platforms multiply. Matter wave interferometers with increasingly massive molecules push coherent path separations where gravitationally induced phases stop being negligible. Levitated nanoparticles cooled close to their motional ground. State promise long free flight times in high vacuum so that tiny gravitationally induced tick rate splits can accumulate. Cryogenic optomechanical cavities explore whether 2 gram-scale mirrors can share quantum correlations that gravity alone could mediate, and space-based atom interferometers stretch the arm time so far that a few parts in 10 to the 18 of gravitational time dilation can be put into play as a controllable knob. Across all of them, the discipline is the same. Map every mundane noise source and then ask whether a leftover signal follows the geometry-dependent scaling that only a genuine superposition of spacetimes would produce. Conceptually, the program brings you face to face with long-standing puzzles in a calmer light. The problem of time in canonical quantum gravity, how to speak of dynamics when the total state is annihilated by a constraint, looks less like a paradox once you accept that time is relational, carried by quantum clocks that can themselves be put into superposition with the systems they time. The complaint that you can't superpose metrics because diffeomorphisms identify them dissolves when you remember that physical predictions are about invariant relations among fields and clocks, not about coordinates. Even the fear that indefinite causal order invites contradictions fades when you track no signaling carefully. Superposed orders can enhance computation and communication tasks, but they cannot be used to send messages to the past or violate causal inequalities once all systems are counted. What does change profoundly is how you talk about events. In a definite geometry, an event is a point where world lines meet. In a superposed geometry, you talk instead about quantum events, correlations that can be sharp in some frames and broad in others, and experiments become about turning those correlations into interference or entanglement that no classical stochastic geometry could mimic. Skepticism is not only healthy, but productive here, because it pushes theorists to make distinctions that guide the bench. A mere superposition of mass distributions is not yet a superposition of geometries unless you can read out a gravitationally relational phase. A mere gravitationally induced dephasing of a composite's internal clocks is not yet decisive unless it cleanly follows potential differences and vanishes in stationary configurations. And a claimed gravity-only entanglement must survive devilish crosschecks with stray electrostatics and Casimir forces. In that spirit, researchers design swap tests, geometry flips, and spin echo-like sequences so that what remains cannot be shrugged off as clever noise. In parallel, theory tightens consistency. Semi-classical, gravity equal average of quantum stress models are shown to block certain entanglement signatures by construction, while fully quantum mediator models allow them. Stochastic collapse variants predict mass and separation-dependent loss with a scaling distinct from purely relational phases, giving you a way to tell superposed spacetime from objective collapse. If you zoom out to cosmology, the question takes on a different face. Quantum fluctuations in the early universe that seed structure are usually computed atop a fixed expanding background. But if you are honest about back reaction at leading order, you are dealing with a squeezed state where matter and geometry share quantum correlations, a gentle, planet-sized version of superposed spacetimes. And precision measurements of the cosmic microwave background already act as a coarse audit of that story. Closer to home, high-precision clock networks linked by optical fibers across continents test the redshift part of the logic by comparing tick rates at the 10 to the 18 level, asking whether concatenated, closed loops of time transfer return exactly to zero as classical geometry demands, or whether a faint, state-dependent residue hints at quantum relational phases in Earth's field. So far, classical geometry wins, which is a triumph for relativity and a clear message for quantum superposition hunters. If you want to see new structure, you must isolate, cool, and choreograph systems where coherence of the geometry-dependent phase is not washed out by an environment that never agreed to play along. Perhaps the most humanly gripping payoff of this whole pursuit is pedagogical. It trains you to ask questions that only make sense in a relational world. What does A's clock say when B's photon reaches C, given that D's mass sat in a coherent split? Which causal order is realized from the perspective of a probe entangled to the field? And it teaches you to separate ore from sloppiness. Superposed spacetime does not mean shimmering multiverses on the wall. It means that the rules for composing durations and distances are themselves subject to quantum composition when the sources of curvature are. The right emotional tone, then, is gentle curiosity backed by engineering grit. The experimental frontier is hard because you are trying to keep a whisper coherent in a storm, but every step, longer free fall, colder traps, better vacuum, smarter noise cancellation, pushes you toward regimes where classical geometry is still correct on average, yet finally loose enough to let its quantum grain show through in interferometric contrast or an entanglement that would be illegal if the field were merely a classical stagehand. When the day arrives, and it may, when two tiny masses entangle through nothing but their mutual pull, or when a clock interferometer returns a visibility curve whose depth tracks a coherent split in proper time, rather than in mere path length, you will not have torn the fabric of reality, you will have learned to see its weave. Until then, the work itself is the teacher. It insists that space and time are not stolid ingredients, but agreements among systems, agreements that can be held loosely enough to explore alternatives and then brought back together to check whether nature kept all the promises at once. And as you let the thought settle, you can keep a simple picture on your desk. A pair of faintly glowing paths in a dark chamber. A bead of matter choosing both for a while. A pair of tiny clocks disagreeing by a whisper, and then reconciling in a fringe. And remember that what is at stake is not spectacle but understanding. Whether the stage we live on is fundamental or a chorus, and how softly we must listen to hear the harmonies in which even geometry sings. Interferometry with massive objects. You don't test whether the world keeps quantum faith by staring at a single atom. You test it by asking a heavy, complicated object to behave like a wave and then making that wave interfere with itself. And interferometry with massive objects is the craft of turning that audacious question into an experiment that can be graded. Begin with the obstacle you can feel in your bones. As mass grows, the wavelength associated with motion shrinks to absurd smallness. So the same slits and light pulses that effortlessly split atoms barely tickle a nanoparticle, and yet researchers have learned to build beam splitters that don't rely on knife-edge slits but on momentum kicks. Standing waves of light that act as phase gratings, pulsed fields that nudge in opposite directions, even patterned ionization that carves a density grating in midair. And with those tricks, they coax large molecules and dielectric spheres into coherent superpositions, whose separate paths later recombine into fringes. To keep the story honest, you must confront every source of blur that wants to erase the pattern. Stray gas molecules that collide and mark which path the object took. Thermal photons emitted by the object itself that act like tiny flashbulbs. Patchy electric fields that tug asymmetrically. And vibrations that smear the relative phase. Each culprit scales differently. Gas decoherence falls with pressure. Blackbody blurring grows with internal temperature and surface area. Jitter adds phase noise proportional to path separation and freefall time, so the art is to cool, evacuate, and quiet the environment until the only remaining difference between the two paths is the one you intentionally programmed. That's why platforms range from near-field matter-wave interferometers that thrive in tabletop vacuums to levitated optomechanical setups where a single nanoparticle is trapped and cooled close to rest, released into freefall, nudged into a split by a sequence of light pulses, and caught again for readout. In the near-field family, you learn to work with very small path separations and short times but exquisite control. A pulsed standing wave imprints an angle-dependent phase on a beam of hot molecules, and a second and third grating, carefully timed, convert that hidden phase into a visible density modulation that you detect downstream. An approach that has carried ever heavier molecules, complete with internal complexity, through interference. In the levitated family, you trade throughput for purity. A single sphere, cooled by light or electric feedback, can enjoy long, silent flights during which even tiny gravitational and inertial phases accumulate. And a final pulse sequence plays the role of a recombiner whose contrast tells you whether coherence survived. The payoffs are immediate and twofold. First, you map how quantum visibility actually scales with mass, size, temperature, separation, and time, replacing slogans with measured exponents. Second, you obtain a tool for precision sensing that responds to acceleration, rotation, and potential gradients with a sensitivity set by the very same phase that builds your fringes, turning the device into a gravimeter or gyroscope whose limits are set by decoherence. You can audit rather than by mysterious noise. To keep from fooling yourself, you adopt contrast management as a discipline. Vary pressure to see the predicted exponential loss from gas hits. Vary internal temperature to watch blackbody decoherence rise and fall. Reverse pulses to cancel unwanted phases while leaving the intended one. And rotate the apparatus to flip Coriolis contributions like a sign test. Along the way, you discover practical subtleties that teach you new physics. Internal vibrational states of complex molecules act like hidden clocks that carry which path information unless you cool or encode cleverly. Surface forces near gratings or mirrors, Casimir and patch potentials, imprint extra phases that can be mapped and subtracted, or if you're ambitious, measured as a signal. Radiation pressure shot noise from the very light that splits and recombines the object sets a fundamental flaw that forces you to balance pulse power against recoil and heating. And because the phase grows with free fall time, you either build tall drop towers, fly the experiment on rockets, or simulate microgravity with magnetic levitation to hold the object weightless while coherence grows. Beyond technique, the philosophical return is clean. Heavy object interference lets you chase scale rather than exotic materials. Push mass up, path separation out, and coherence time long, and watch whether visibility shrinks exactly as ordinary. Counted decoherence predicts, or whether an extra, size-dependent loss appears that can't be blamed on the usual suspects. If nothing odd shows up, you've strengthened the case that quantum linearity survives deep into the mesoscopic world. If a residual, geometry-blind blur remains that resists echo tricks and vanishes tests, You have evidence that the world adds a new rule when too much stuff travels two ways at once, even without surprises. The metrology dividends are real. Molecular interferometers weigh polarizabilities and permanent dipoles with parts per thousand precision. Nanoparticle devices measure tiny force gradients and local accelerations that rival classical sensors while occupying a fraction of the volume. And hybrid schemes that use spins as internal gyroscopes, alongside center of mass interference, let you separate inertial and gravitational phases in a single shot. What keeps this field honest and beautiful is that everything that can spoil the interference is also a handle you can turn. Heat can be lowered by smarter materials and radiative cooling, pressure by better pumps and cryogenic walls, jitter by quiet platforms and common mode rejection, stray fields by careful grounding and symmetric designs. The frontier, then, is not mystical, but methodological. Building a quiet enough laboratory, sometimes in orbit, to let a heavy object carry a clean phase across a long, silent flight, and then asking it the simplest question nature understands. Did both paths happen? And if so, how did the world keep the book? When the fringes answer, they do so with humility rather than fanfare. A rise in contrast when you've cancelled a noise source correctly, a fall when you deliberately turn it back on, a phase shift that tracks a gentle tilt of the Earth, or a minute change in local mass, all of it adding up to a picture where quantum mechanics is not a parlor trick of the very small, but a rule that survives contact with weight, complexity, and time. And as the lights dim on the apparatus, the lesson for you is quiet but durable. Coherence is a resource that heavy things can carry if you give them room, and interference is the journal in which they write what happened. Give them better vacuum, colder starts, softer hands, and longer falls, and they will keep writing, one fringe at a time, until the line between wave and object stops feeling like a border and becomes, as it truly is, a matter of how gently you look. Gravitationally mediated entanglement tests. You don't prove that. Gravity is quantum by catching a graviton in a jar. You prove it by letting two tiny objects whisper to each other only through their mutual pull, and then showing that afterward they share correlations no classical messenger could have delivered. And gravitationally mediated entanglement tests turn that audacious idea into a plan with knobs you can actually turn. Prepare two neutral, well-shielded masses so that each one travels in a controlled superposition of nearby paths. Keep all other forces dormant. Let the masses sit close enough and long enough that the slight difference between near-near and near-far branches imprints distinct phases through the Newtonian potential, and then recombine and read out auxiliary tags, often spins or internal states, that report whether the joint state carries entanglement. The logic is crisp and state-of-the-art. If the only allowed interaction channel is classical, meaning it can be modeled as a measurement and feedback link that never carries quantum coherence, then it can at most add noise or classical correlation. It cannot create entanglement between systems that began unentangled. Observe entanglement under conditions that rule out every other mediator, and you've shown that whatever field carried the influence had quantum capacity, which is exactly what gravity is quantized enough to entangle means at laboratory scales. Turning that into hardware demands ruthless honesty about nuisances, so the leading protocols are built like lockboxes. Use materials with vanishing magnetic susceptibility and painstaking charge control to silence electromagnetism. Coat and cool surfaces to tame patch potentials and Casimir forces. Bury everything in cryogenic, ultra-high vacuum so residual gas and blackbody photons don't act as gossiping witnesses. Mount the two interferometers on independent stages and run common mode rejection so seismic jitters don't fake phases. And split each mass with spin-dependent kicks, Stern-Gerlach style or equivalent, so a clean on-off superposition lever exists that you can flip for controls. The witness too is chosen for realism. Full tomography is overkill and fragile, so you calibrate a simple entanglement indicator from 2 or 3 spin bases, or use a Bell-type inequality tailored to your geometry, then demand the right scalings. The signal must grow with interaction time, fade with separation, and flip sign when you invert which branch sits closer. Do that and you start to separate wheat from chaff. Stray electric fields scale with charge and surface texture, not with mass alone. Acoustic crosstalk vanishes when you detune suspensions. Light leakage produces phases. You can refocus with echo pulses, whereas the gravitational relational phase survives such refocusing. Engineers add geometry flips, swap the mass's positions mid-run, species swaps, use different materials to check magnetic tails, and distance toggles, step the gap in small increments and fit the curve, so any surviving entanglement can't hide behind a single neat excuse. Platforms diversify to hedge bets. In spin mass schemes, each nanoparticle's path is tied to an embedded spin that you read out with optical or microwave pulses. While in purely mechanical schemes, two levitated spheres exchange their pull and you infer entanglement from correlated motion and light phase without spins at all. Optomechanical cavities add sensitivity by turning femtonewton tugs into measurable phase shifts, but must prove that the photons that read out each mass don't themselves ferry quantum information across. So designs enforce strict spatial and spectral separation of meters and run meter swap controls to catch any cheating. In every case, the scales are demanding but human. Objects hefty enough to feel each other, yet small enough to keep coherent. Nanoparticle to micron regimes. Separations you can see under a microscope, and interaction times long compared with mechanical periods, but short compared with ordinary decoherence. Theory has kept pace with concrete falsifiability. Semi-classical gravity models that feed quantum expectation values into classical fields are shown to forbid entanglement under clean assumptions, so a positive result would close that door. Conversely, collapse or classical noise alternatives predict visibility losses that don't revive under echo tricks and don't follow the distance-time law of a coherent gravitational phase, providing distinct failure modes that experiments can target. Even the background of the real universe cooperates. Tidal gradients across millimeters are stable and characterizable. Gravitational wave hum at these frequencies is negligible, and Earth's field just provides a gentle bias you can subtract or exploit. None of this means the test is easy. Charges must be measured and neutralized to the last electron. Magnetic tails must be mapped and mu-metalled into silence. Patch potentials must be calmed with careful coatings and long bakes. And vacuum and cryo must turn the chamber into a quiet winter night. But it does mean the road is straight. Push coherence time up, temperature down, and distance control into the regime where gravity's phase can finally outrun everything else. What would a win mean, and what would it not mean? A win would not hand you a full quantum gravity theory or a particle picture of the graviton, but it would say that at accessible energies the gravitational field supports quantum superposition and can transmit entanglement, ruling out purely classical channel explanations and forcing any completion of gravity to respect that minimal quantumness. A null result, if achieved in conditions that decisively bury all mundane dephases, would be just as interesting, tightening bounds on how gravity couples to superpositions and shunting attention toward objective collapse or hybrid models that must then face consistency checks with energy conservation and no signaling. In either outcome, the collateral science is rich. The same rigs become exquisite probes of tiny forces, absolute gravimeters in volumes the size of a shoebox, and testbeds for noise budgeting that will benefit quantum sensors far from gravity's frontier. Let the idea land with the right tone. This is not a quest for spectacle, but for clean inference. Two quiet masses, two quiet paths, a long lawful wait, and a readout that either crosses the classical ceiling or does not. If it does, the sky over tabletop physics gets a new constellation. Tiny, engineered stars whose only light is the entanglement they share through the dark. And if it doesn't, the night gets clearer in a different way, with whole families of stories crossed off and better ones invited in. Either way, you learn to ask gravity a new kind of question. Not how hard do you pull, but can you keep a secret between friends? And the answer, when it comes, will be modest in volume but large in meaning. A whisper that decides how we talk about space, time, and the quietest bond in nature, vacuum energy and the cosmological constant. You first learn to call emptiness nothing, but physics keeps handing you receipts that the vacuum is not a blank at all. And the most audacious line item on that receipt is a tiny, persistent pressure that seems to push the universe apart, the cosmological constant. So let's walk into this carefully. From the doorway to the back room and out again with a clearer bill. Start with a sober fact about the large-scale universe. Distant galaxies are not just receding because of initial momentum. The expansion is accelerating, which means there is a component of the cosmic energy budget whose pressure is so negative that it overwhelms the gravitational pull of ordinary matter and light. The simplest way to model that is to add a constant energy density to the right-hand side of gravity's equations, a uniform something that looks the same everywhere and everywhen, whose pressure is fixed to be as negative as its energy is positive, and that pair of properties together act like a steady hand that stretches space faster and faster. On the quantum side, the vacuum you imagined as empty is actually seething with zero-point fluctuations, the lowest energy jitters of every field we know, and because these jitters are Lorentz invariant on average, no preferred direction, no preferred rest frame. The stress they contribute must be proportional to the metric itself, which is a highbrow way of saying quantum fields naturally produce a term that gravity would read exactly like a cosmological constant. The trouble is, in the accounting, if you estimate that vacuum energy by summing up all those jitters up to some high energy cutoff, you get a number so enormous that it would have curled the universe into a microscopic ball long ago, dozens of orders of magnitude too big, compared with what we actually infer from supernova light curves, the microwave background's harmonic pattern, and the way galaxies cluster on large scales. That mismatch is not a cute discrepancy. It is the starkest fine-tuning problem in fundamental physics. The observed value is roughly 1 part in 10 to the huge relative to naive expectations, as if a cosmic bookkeeper cancelled an immense charge with an immense credit to leave a whisper that only cosmology can hear. So how do we thread the needle between vacuum has structure and acceleration is tiny but real without lying to ourselves? One pragmatic answer is renormalization. In effective field theory, you are always allowed to add a counterterm to your equations that soaks up the big, cut-off-dependent part of the vacuum contribution, leaving a finite remainder that you fit to observation. And in that language, the cosmological constant is a parameter you fix once. Like the mass of an electron, not something you recompute every time you change microscopes. Honest practitioners wince, though, because even if the bookkeeping is consistent, it doesn't explain why the finite remainder is so small, especially after cosmic phase. Transitions, like those that gave particles, masses should have shifted it by huge amounts, and why it happens to be comparable, today of all times, to the energy density in matter. This is the why now, or coincidence problem, the universe's awkward timing that invites deeper explanation. From there, the ideas branch like careful hypotheses in a lab notebook. One family asks for a symmetry that forces the vacuum energy to vanish, or nearly vanish. Supersymmetry once promised exact cancellation between bosons and fermions. But because that symmetry is broken in our world, the leftover is still far too big unless breaking happens at implausibly low scales. Another family rewires the gravitational response itself, sequestering mechanisms that prevent vacuum energy from gravitating in the usual way by tying it to global variables, or modified gravity models that mimic acceleration without a true cosmological constant, each elegant on paper but pressed hard by data that track not just the expansion rate but the growth of structure and the bending of light. A third family says the constant isn't really constant. It's a field slowly rolling down a flat potential, quintessence-like ideas, which softens fine-tuning in a different place, but at the cost of new degrees of freedom that must be invisibly coupled, stable, and consistent with the near-perfect equation of state we measure to be very close to -1 with little room for drift. The most controversial family leans on selection. Perhaps in a broader landscape of possibilities, say, different vacuum choices in a deeper theory, only those with a small effective cosmological constant grow galaxies and observers. So we find ourselves in a rare but allowed patch. That story has the awkward virtue of fitting the magnitude without offering a dynamical mechanism, and it is only as compelling as the independent evidence we can muster for the underlying landscape. Someone then raises a common-sense hand about laboratory physics. If vacuum energy gravitates, why doesn't the Casimir effect, which measures vacuum differences between plates, weigh in a way we could detect? The reply is that Casimir shifts are relative changes confined between conductors, while the cosmological constant is about the absolute all-of-space baseline. Bound systems like atoms, planets, and even galaxies are oblivious to tiny uniform energy densities because local forces and curvature dominate. So the cosmological constant's influence shows itself only on scales where the fabric's average tension matters. The intergalactic, horizon-sized scales that cosmology surveys best. On the observational front, the story is tight but alive. Independent measurements, standard candles, standard rulers, the pattern of temperature and polarization in the background radiation, weak lensing maps that trace the scaffolding of dark matter, converge on a universe where roughly 2/3 of the energy density sits in this smooth, negative pressure component, with current bounds saying its equation of state parameter hugs -1 within small errors. Ongoing and next-generation projects push two levers at once. They sharpen our map of the expansion history across time, and they track how structures of different sizes grew under that history. Together, those levers can sniff out small deviations from a true constant, time, variation that would favor fields over a pure, cosmological term, or subtle tensions between how space expands and how gravity pulls on inhomogeneities, which would hint that we mismodeled gravity itself. There's even a thermodynamic face to the problem that, while not a solution, changes your intuition. A universe dominated by a positive cosmological constant tends toward a de Sitter phase with a horizon that carries its own temperature and entropy, a kind of ultimate heat death with a finite information budget. So the constant is not just a parameter, it is the long-term climate of reality, whether our vacuum is truly stable in that climate, whether quantum tunneling to a deeper state is even meaningful once you fold in gravity, and how the notion of de Sitter entropy meshes with microscopic counts are live technical questions that keep the theoretical conversation honest. What should you, as a careful learner, watch for next? 3 kinds of evidence rise above the noise. Precision tests that keep corralling the equation of state around -1 while ruling out time dependence, and couplings that would have shown up as new forces or as violations of energy conservation in astrophysical systems. Consistency tests that compare expansion and growth, hunting for mismatches that would force us toward modified gravity or unorthodox interactions, and integrated signals like the late-time imprint of decaying gravitational potentials on the microwave background, which depend directly on how the background acceleration and structure growth talk to each other. If the cosmological constant remains a perfect fit, the mystery will not fade, but it will be fenced. We will know that whatever deeper explanation exists must land on an almost exact constant at late times with astonishingly small dimensionful value. If, however, a clean repeated deviation appears, say, a modest drift in the equation of state that stubbornly resists systematic error, then entire classes of field models move from speculation to engineering, and laboratory searches for feeble couplings become targeted rather than generic. Let the mood at the end be steady rather than breathless. Vacuum energy and the cosmological constant is where 3 kinds of understanding meet. Quantum fields insisting the vacuum is lively, gravity insisting that even uniform liveliness weighs, and observation insisting that the weight is tiny but non-zero. And our job is not to pick a favorite story, but to keep them in dialogue until they agree. Along the way, you learn to separate metaphors from mechanics. The vacuum is not a fluid in a pipe, but it has an equation of state. To respect the power of effective descriptions. Renormalization is not a dodge, it is a language. And to accept that sometimes the most impactful numbers in physics are not the largest ones we can imagine, but the smallest ones that survive every cancellation. The cosmological constant is one of those small survivors, a whisper that shapes the fate of everything. And whether it turns out to be a brute fact, a symmetry's leftover, an emergent bookkeeping trick, or a signpost to a wider landscape, the discipline you gain by chasing it, balancing theory against measurement, cosmic scales against quantum intuitions, is already part of what it means to understand a universe that writes even its silence into the equations. Inflation's quantum seeds for structure. You begin with the quietest idea in modern cosmology, that the largest structures you see today were born as the smallest possible ripples, quantum jitters in a field when the universe was a fraction of a second old. And inflation's quantum seeds for structure is the name of that audacity made precise. Take a patch of the early universe and let it undergo a brief spell of accelerated expansion so violent that wavelengths far smaller than an atom are stretched to astronomical size. Then watch how those tiny fluctuations, once flung beyond the horizon where local forces can no longer smooth them out, become frozen patterns in the density and in the geometry itself, to be released later as the scaffolding for galaxies, clusters, and the cosmic web. You can feel this without symbols if you imagine a calm pond that suddenly expands faster than ripples can follow. Each ripple's crest is pulled so far from its neighbor that the water between them hardly has time to respond. So the pattern stops evolving and becomes a snapshot, a record of quantum chance turned into classical initial conditions. When the expansion relaxes and ordinary hot Big Bang evolution resumes, those frozen ripples re-enter the horizon as gentle over and under densities that gravity can amplify, and the radiation and matter they stir respond like a resonant drum. Photons and baryons slosh, leaving a series of acoustic imprints that we still see as a regular set of peaks in the cosmic microwave background's temperature map, and as a preferred spacing of galaxies, evidence that the seeds were laid down with extraordinary coherence. The most striking part of this story is how specific it is despite the violence. The spectrum of fluctuations is predicted to be almost, but not exactly, scale invariant, meaning you get nearly the same amount of power on many scales with a slight tilt that reveals how quickly the inflating energy density was rolling down its potential. The statistics should be almost, but not exactly Gaussian, with any three-way correlations so small that they become precision targets rather than loud signatures. And because gravity itself carries quantum fluctuations, inflation generates a background of long wavelength gravitational waves that imprint a distinctive curling pattern in the microwave background's polarization if they're strong enough, a telltale B mode that would act like a fossil from the very first moments. Hard to see, easy to fake with dust and lenses, but so diagnostic that experiments keep pushing toward it, because a detection would not just decorate the theory, it would weigh the energy scale of the beginning's engine. The same framework quietly explains puzzles that used to look like metaphysics. Why the universe looks so smooth across regions that never had time to talk, inflation lets them share a past. Why its geometry is so close to flat, the exponential stretching irons out curvature like a wrinkle under a hot iron. And why the temperature fluctuations are so coordinated across the sky. Modes of many sizes were laid down with synchronized phases as they froze. But inflation is not one model, it's a discipline. Many candidate engines can drive the acceleration from a single slowly rolling field to multiple fields that can trade energy or imprint their own signatures. And that variety matters because each choice changes the fine print. Multi-field versions can produce extra isocurvature fluctuations that shift relative amounts of matter and radiation. Features or kinks in the potential can leave ringing patterns in the spectrum, and non-trivial interactions among the fields can generate specific shapes of non-Gaussianity that future surveys know how to hunt. The transition out of inflation, reheating, is another place where physics leaves fingerprints. As the inflating field hands its energy to ordinary particles, the details of that handoff affect the starting temperature of the hot Big Bang and can seed subtle departures from perfect equilibrium that precision, nucleosynthesis, and background radiation measurements can constrain. The delicate bridge from quantum to classical is often presented as a mystery, but in this context it is a workhorse. As modes are stretched beyond the horizon, they become enormously squeezed, so their quantum phases align in a way that makes them effectively classical random variables for any local observer. and interactions with the flood of shorter wavelength modes act like an environment that decoheres the long modes without needing an external measuring device. That is why we can treat the initial conditions as classical maps and still claim an authentically quantum origin. Not a contradiction, but a chain of physical processes with calculable timescales and rates. Observationally, the case is strong and still strengthening. The pattern of acoustic peaks in the microwave background lines up with the predictions of coherent, adiabatic initial conditions. The overall tilt is gently red, as slow-roll dynamics would expect. Maps of large-scale structure reveal the same primordial power spectrum transplanted into the distribution of galaxies, and cross-checks that tie the expansion history to the growth of structure keep preferring the same picture with no wild departures so far. Yet humility is not optional. We have not seen the gravitational wave fossil decisively. Non-Gaussianity is small enough to keep many models alive, and tensions among datasets at the percent level still nudge us to check for systematics or for modest extensions. Alternatives to inflation, scenarios where a contracting phase precedes a bounce, or where the vacuum state is modified, or where gravity differs from Einstein's in subtle ways, have learned to make similar large-scale predictions. So the real discriminants are now in the details. The exact shape of any non-Gaussian signal, the presence or absence of isocurvature contributions, the running of the tilt across scales, and the polarization pattern's fine texture. This is good news, not frustration, because it turns how the universe began into a laboratory problem. Build better detectors, map more sky, simulate more carefully, and ask sharper questions that multiple teams can answer independently. Through this lens, the philosophical message grows gentle rather than grandiose. Inflation does not claim to explain everything. It explains why the universe could be so simple to describe on large scales and so richly structured within that simplicity. And it does so by turning quantum indeterminacy into a productive randomness whose footprints we can still read. It invites you to trade myth for mechanism, horizon problems for causal histories, flatness for dynamical smoothing, structure for amplified vacuum noise, and it asks for accountability at every step, from the potential that drove the expansion to the particles that reheated the world to the statistics etched in the oldest light. Whether the final story is a single-field slow roll, a multi-field landscape with gentle turns, a phase that imitates inflation's virtues through another engine, or something we have not drawn yet, the learning is already durable. The largest patterns in the sky began as the smallest whispers, and the fact that we can predict their shapes, measure their spread, and argue over their tiny departures is not an accident. It is the signature that the early universe, however strange, obeyed rules we can test. Carry that as the closing cadence. The night's mottled glow, the web of galaxies, the quiet regularity of acoustic peaks are not just scenery. They are the interference fringes of the beginning, set by quantum seeds, stretched by a brief wind, and preserved by the long cooling breath of cosmic time.